2 blackouts back to back the first one. Everyone remembers the October 1st US government shutdown that made headlines across the nation. But the second, that's the one that flew under the radar, the one that barely anyone knows even happened. September 1st marked the day a billion-dollar spacecraft locked onto one of the most bizarre visitors our solar system has ever encountered. The critical moment arrived on September 3rd, and right when history should have been made, the cameras went completely dark. Not for hours, but for days. That opportunity vanished into thin air. Accident or intentional, what could NASA have? Witness that demanded absolute silence. Tonight, we're peeling back the layers on this blackout. And what emerges isn't just unceremonious, concrete proof of what many of us have suspected about this interstellar visitor all along. If these revelations are sending shivers down your spine like they are mine, smash that like button and subscribe right now so you don't miss a single update as this story unfolds in real time. Drop a comment with where you're watching from, what time it is there, and whether you think we're getting the full story or just the version they want us to swallow. And if you want to help push this community forward, share this video on X, Facebook, Reddit, even your own group chats. The reason we can keep chasing stories like this. Thanks for having our backs. Part 1. The Missing Days. NASA pulled the plug on its feed. Not the entire space program, not the internet. But something very specific went down in the first week of September 2025 that we still can't fully wrap our heads around. A spacecraft called Psyche, a mission launched to study a metal asteroid millions of miles away, was scheduled to photograph something that came to visit us from interstellar space. That something was an object called 3 Artless. And according to NASA's own public schedule, Psyche was supposed to capture images of this visitor around September 3rd or 4th, 2025. But here's where things get weird. When researchers went hunting for those images in NASA's public archive in the raw image database, where every photograph Psyche takes is supposedly uploaded for the entire world to see, they came up empty-handed. No images from September 1st, no images from September 2nd, no images from September 3rd or 4th, no images from September 5th. The archive simply went silent. Then on September 8th, the images started flowing again. 3 days, a 72-hour gap, in a spacecraft's publicly available data during one of the most anticipated astronomical events of the year. And nobody officially explained why. The Psyche spacecraft itself isn't some forgotten probe gathering dust in a corner of the solar system. This is a cutting-edge mission funded by NASA with hundreds of millions of dollars, equipped with high-resolution imaging cameras capable of capturing metallic surfaces in stunning detail. The whole reason Psyche was built was to get up close and personal with a metal asteroid named 16 Psyche and photograph it with precision that would rival some of the best cameras on Earth. So this spacecraft, this technological marvel, was perfectly positioned to observe 3I Atlas as it passed through our neighborhood. NASA's own publicly posted mission overview specifically listed 3I Atlas as one of Psyche's planned targets. It wasn't a secret. It wasn't classified. It was announced. And then when the moment came, when the spacecraft was positioned and ready, when the window of opportunity was wide open, the images disappeared from public view. So what exactly is 3I Atlas? It's an interstellar object. That means it didn't originate from our solar system. It came from somewhere else in the galaxy, traveling through the void of space at tremendous speed. And in 2025, it passed close enough to Earth that scientists everywhere wanted to study it. We don't get many chances to examine visitors from the stars. When they arrive, the entire astronomical community telescopes point upward. Spacecraft adjust their orbits. Data flows in real time. This is the kind of moment that shapes scientific understanding. This is the kind of moment that makes discoveries, except this time for those crucial 3 days. Nothing flowed at all. Community researchers, astronomers, and space enthusiasts who monitored these archives regularly noticed the gap immediately. They flagged it, they discussed it online, they asked questions, but NASA offered no official explanation. Not a comment about a technical malfunction, not a statement about data processing delays, not even a simple acknowledgement that the gap existed. The agency simply allowed the silence to remain. Now, someone might argue that the gap could have been caused by the United States government shutdown, scheduled for October 1st, 2025. Maybe data backup systems failed. Maybe something about the shutdown affected the archive. But that doesn't make sense. The shutdown happened in October. The gap happened in September. An event that occurs after something cannot explain something that happened before it. The timeline doesn't support that explanation, so we're left with a mystery that belongs to no external event. No scheduled maintenance window, no known technical failure. It's a gap that, as far as we know, nobody has ever adequately explained. Consider what this means for a moment. Consider that we live in an age of radical transparency in space science. Every image from the James Webb Space Telescope is published. Every photograph from the Mars rovers appears online within hours. Every data point from a dozen different space agencies flows to the public archives almost automatically. Yet here, in this specific case, during this specific window with this specific object, the system simply shut down. The question becomes not just what happened, but why. Did Psyche fail to point at 3I Atlas as planned? Did the camera malfunction at exactly the wrong moment? Did something else entirely occur that we haven't been told about? Or, and this is the thought that lingers, did the images get taken and then deliberately removed from public access? What would cause an agency to make that choice? We don't yet know. But we're about to discover that this gap is not an isolated incident. This is the beginning of a pattern. This is the first thread in a much larger tapestry of silence, delay, and mystery that stretches across multiple space agencies, multiple missions, and multiple weeks. This is the opening of what we might call the blackout. And as we pull that thread, the entire landscape of what NASA and ESA have been doing with 3I Atlas. Data starts to unravel in ways that challenge everything we thought we knew about transparency in space science. Part 2. ESA's 2099 glitch in April 2026 lockbox. While NASA's Psyche probe was going dark over Earth, something equally strange was happening on the other side of the Atlantic. The European Space Agency which operates a spacecraft called the ExoMars Trace Gas Orbiter, or TGO, was also supposed to have access to 3I Atlas as the object moved through the inner solar system. The ExoMars mission normally releases its data to the public within months of collection. Scientists can download images, spectra, and raw measurements. The system is designed to be open. It's designed to be shared. But when researchers looked at ESA's data archive for 3 Atlas observations, they found something that made them pause. The release dates for certain data sets were listed as the year 2099. That's not a typo. That suggests a processing delay of a few weeks or even a few months. That's a date that sits 74 years in the future. It's the kind of timestamp that, for all practical purposes, locks the data away forever. Or at least, it locks it away for a period of time so long that most of us won't live to see the information released at first. Many researchers assumed this was a simple metadata glitch, a software error where dates got corrupted or default timestamps got filled in incorrectly. These things do happen in complex information systems. But then something else happened. The dates changed. Not all of them went away, but many of them shifted to a new timestamp, April 3rd, 2026. Suddenly, instead of waiting until the year 2099, researchers were being told they could expect these datasets on April 3rd, 2026. That's 5 months earlier than today. Well, it was 5 months at the time the announcement was made. Now, it's closer. But this creates a problem because April 3rd, 2026 is still a significant delay. It's months away. It's a lockbox. The contrast between NASA's approach and ESA's approach is instructive. NASA simply removed the images from public view and said nothing. ESA at least acknowledged that the data exists and that it will be released at some point. But the very fact that ESA felt compelled to set a release date so far in the future raises uncomfortable questions. Why would any space agency deliberately delay the release of scientific data by 6 months or more in the normal course of operations? Data about comets and asteroids and interstellar objects flows to the scientific community almost immediately. Yet here, both agencies seem to be operating under different rules. NASA's silence could be interpreted as a technical glitch, but ESA's deliberate date setting the fact that someone in their organization specifically chose April 3rd, 2026 as the release date suggests something more intentional. When you examine the history of space missions, you do find precedents. For long embargoes, the Hubble Space Telescope in its early years had a period where data was released to the team that had requested the observations first before being made publicly available. Some Mars rover images have been delayed for scientific processing, but these embargoes typically last weeks or months at most. 74 years is in a category all by itself. 74 years is not a processing delay. It's a decision. It's a choice to lock something away so thoroughly that it effectively disappears from public consciousness. The stated reason when ESA eventually addressed the issue was tech in a metadata problem, a glitch in their system. But the 2099 date raises a different possibility entirely. What if that wasn't a mistake at all? What if someone somewhere deliberately set that date as a way to hide the information in plain sight? What if a placeholder for classified or sensitive data got left visible in the archive and then had to be cleaned up when people noticed? We can't know for certain, but the timing, the deliberation, and the shift from one time stamp to another suggests that somebody was making choices about what the public would and would not see. The implications are staggering. If both NASA and ESA were handling 3I Atlas data differently from their normal protocols, if both agencies seem to be delaying or withholding observations, then we're no longer looking at isolated technical problems. We're looking at a pattern. We're looking at something that both organizations deemed significant enough to treat specially. And the question becomes not just what happened, but what did they see that made them decide to lock the data away? What observation required a lockbox? What image or spectrum or dataset compelled both a European agency and an American agency to suddenly change their normal procedures for public transparency? The answer to that question might lie in what the object itself was revealing. Because around the same time these archives were going dark, new images and spectroscopic data about 3I Atlas was starting to emerge. And what those images showed was something that no comet had any business showing at all. Part 3, the Sunward Jet confirmed. In August of 2025, new imagery of 3I Atlas became available to researchers. The observations came from ground-based telescopes and from space-based instruments, and when scientists examined the photographs, they saw something that made them sit up straight. There was a jet of material toward the sun. Now, anyone with basic knowledge of comets knows that this is not what is supposed to happen. When a comet approaches the sun, the heat causes ethers to sublimate. Those ethers turn to gas and dust, and the radiation pressure from the sun's light pushes that material outward away from the star. That's why comets have tails that stream behind them like hair blown in the wind. The tail always points away from the sun. It's as fundamental to comet physics as gravity is to falling objects. Except 3I Atlas didn't seem to care about this rule. The spectroscopic data was equally strange. Researchers using the Keck Observatory in Hawaii collected light from 3I Atlas and analyzed it. The results showed emissions of nickel and cyanide, elements that do appear in some comets, but rarely in this particular combination. The object also displayed what scientists called an antitail, a secondary tail that forms in front of the primary tail, but in this case pointing in an unusual direction. The behavior didn't match any standard comet model. It was as though something was actively pushing material toward the sun rather than having the sun push material away. Think of the difference between wind pushing leaves outward from a tree and a leaf blower deliberately directing air inward. The sun is supposed to be the leaf blower. The sun is supposed to do the pushing. But 3I Atlas seemed to have its own mechanism. When you combine this sunward jet observation with earlier data from the James Webb Space Telescope that showed 3I Atlas's atmosphere was dominated by carbon dioxide, the picture becomes even stranger. A carbon dioxide-rich coma suggests the object formed near what astronomers call the carbon dioxide ice line, a region in a protoplanetary disk where carbon dioxide would freeze. This is an unusual chemistry for a comet that supposedly originated in the Oort cloud, the reservoir of icy bodies surrounding the solar system. It's unusual chemistry for something that came from interstellar space. It's the kind of chemistry that raises questions about where this object really came from and what Mechanisms have been shaping its behavior. The sunward jet, in particular, haunted the minds of anyone studying the data. A jet pointing toward the sun is not easily explained by natural comet physics. But imagine for a moment a spacecraft. Imagine a vessel traveling through space that needed to dump excess heat or maintain its orientation. A craft pointed toward the stars might vent material toward the sun as a way to recharge, to absorb radiation, or to maintain stability. The direction matters in such scenarios. It's not random, it's purposeful. The timing of this observation release was also peculiar. The august image came out just as Psyche was preparing to observe 3I Atlas in September. The spectroscopic anomalies had already been noted by the scientific community. Everyone knew that this object was behaving strangely. Everyone knew that it displayed properties that did not fit the standard models. And then precisely when a spacecraft with some of the finest imaging equipment in human history was about to take an even closer look, the data flow from that spacecraft stopped. The archive went dark. 3 days of silence. The August observations had whetted everyone's appetite. They had revealed something fundamentally odd about this object. And just when the obvious next step would be to follow up with higher resolution imagery from Psyche, that information vanished. The sunward jet is not just an anomaly, it's a signature. It's the kind of behavior that leads scientists to ask what is happening beneath the surface. When you see a jet pointing the wrong direction, when you see compositions that don't match expectations, when you see an anti-tail that defies conventional explanations, you start to wonder if you're looking at something natural or something else entirely. You start to wonder if this object is behaving according to the laws of physics as we understand them, or if it's behaving according to some other logic, some other purpose. And if that's what Psyche captured, if that's what the images showed, then it becomes clear why those images might have been locked away, because they would have raised questions that the agencies might not be prepared to answer. They would have forced a reckoning with something the scientific community was not yet ready to discuss. And so the silence deepened. Part 4. The silence from Psyche. After September 8th, when the Psyche archive resumed its normal flow of images, the spacecraft kept taking photographs as it always did. But if you searched through every image that Psyche captured, if you looked through every blog post that NASA published about the mission, if you scoured the social media accounts of project scientists and engineers, you would not find a single follow-up mention of 3I Atlas. There was no discussion of what Psyche saw during its approach window. There was no release of detailed imagery. There was no scientific paper submitted to peer review describing the observations. There was simply nothing. The silence was not just in the archive, it was everywhere. This absence is particularly striking because just weeks before September, scientists involved with the Psyche mission had been publicly enthusiastic about the opportunity to observe 3I Atlas. There were interviews, there were explanations of what the spacecraft could do, how its cameras could capture detail, what kinds of science might be possible if the alignment worked out. The opportunity had been marked on calendars. The community had been prepared. And then, after the window passed, all of that disappeared. The scientists went quiet. The mission website made no mention of it. It was as though the entire observing campaign had been erased from the official record. Several possible explanations could account for this silence. The most straightforward is a technical failure. Perhaps Psyche's cameras were pointed elsewhere when 3i Atlas was at the optimal viewing angle. Perhaps there was a telemetry loss. Perhaps the spacecraft experienced some kind of malfunction that prevented it from capturing the data. These things do happen in space operations. Spacecraft are complex machines operating in an unforgiving environment. But if that were the case, NASA would normally issue a statement explaining what happened. They would say something like, "Our spacecraft was pointed toward this target, but experienced a brief communications glitch, or Psyche successfully imaged the object. But technical issues prevented downloading the full dataset." These statements are routine. They are part of normal mission operations, but nobody made any statement at all. Another possibility is that the data required internal review. Perhaps Psyche captured something unexpected, something that scientists wanted to examine more carefully before sharing with the public. Perhaps the images showed anomalies that triggered a requirement for calibration, review, or peer assessment. This too is not unknown in the history of space missions. The Galileo spacecraft back in the 1990s captured images of Jupiter's moons that revealed unexpected geological features. Researchers spent months analyzing and double-checking before publishing. But even in those cases, agencies issued statements explaining that analysis was underway. They prepared the scientific community for a delayed release. They did not simply vanish into silence. The third possibility is more troubling. It's the possibility of classification. If Psyche captured images showing unexpected structure or unexpected properties on 3i Atlas, images that suggested the object might be something other than a natural comet, then those images might have been deemed sensitive from a national security perspective. They might have been locked away under classification procedures. This too has precedent in the history of space observation. Early reconnaissance satellites returned images that were classified for decades. Even some of the Apollo mission audio recordings were restricted from public access until researchers fought for their release. If an image suggested that an object in space might be artificial, might be of non-natural origin, that would absolutely trigger a higher level of classification. The implications would be extraordinary. The ramifications would be enormous, and the decision to lock such an image away would be made at levels far above any individual mission control room. The cumulative effect of this silence is to create a void in our knowledge precisely at the moment when we should have had clarity. We have August spectroscopy showing an object with anomalous properties. We have a spacecraft positioned to capture high-resolution imagery. We have a scheduled observation window, and then we have nothing. The void is deafening. It's a silence that screams. It's the absence of information acting as information itself. Because in the modern era of radical transparency in space science, silence like this does not happen by accident. It happens because someone decided it should happen. Someone made a choice to not share something that the world was expecting to see. And that choice in itself is perhaps the most important data point of all. It tells us that something happened that someone did not want us to know about. Part 5. The timeline gap. Let's construct a unified timeline of events across all of the space agencies involved. Let's lay them out chronologically and see what shape emerges from the pattern. August 2025 is when new spectroscopic observations of 3i Atlas become available to the scientific community. The KEK Observatory in Hawaii captures light from the object and reveals nickel and cyanide emissions. The compositions are strange. The behavior is not matching textbook comet physics. Scientists begin to discuss what they are seeing. Blogs and preprints start circulating. The astronomy community is buzzing with questions about this visitor from another star. The James Webb Space Telescope also contributes data showing a carbon dioxide-dominated atmosphere. Further deepening the mystery, late August of 2025 brings a high-resolution image of 3I Atlas. This image clearly shows a jet of material pointing toward the Sun, contradicting everything we expect from comet physics. The sunward jet is now visual evidence. It's not just a spectrum or a measurement. It's a photograph. It's something you can see, and everyone in the astronomical community sees it. Everyone is discussing it. Everyone is preparing for the next opportunity to gather more data. Then we arrive at September 1st through 5th. This is the blackout window for NASA's Psyche spacecraft. No images from the spacecraft appear in the public archive during these 5 days. The window encompasses the scheduled observation date of 3I Atlas, September 3rd and 4th. Psyche, which has the capability to photograph metallic surfaces with extraordinary precision, captures nothing that the public can access. On September 8th, the archive resumes. Images appear again, but no images of 3I Atlas are among them. No images of the object have ever appeared in any public database. As far as anyone has been able to find, October 1st, 2025 brings the United States government shutdown. But this cannot explain the September gap. A future event cannot cause a past event. The shutdown is a red herring in this timeline. It's a possible explanation that doesn't work. October 3rd through 7th brings a significant astronomical event. NASA's ExoMars Trace Gas Orbiter comes closest to 3I Atlas as the object approaches Mars. The spacecraft has instruments capable of capturing detailed data. Researchers from the European Space Agency and international collaborators should have been preparing to analyze these observations. Should have been because the data from this flyby has not yet appeared in any public database. The European Space Agency stated that the information would be available on April 3rd, 2026. That's months away. That's a lockbox. October 25th and 26th bring another deadline. NASA's Europa Clipper mission has windows to observe 3I Atlas in late October. The spacecraft is heading to Jupiter's moon, Europa, but has high-resolution imaging equipment that could photograph an interstellar visitor if properly directed. Will we see those observations? Will the data appear in the archive? Or will October bring another silence? April 3rd, 2026 is the currently scheduled date for ESA to release 3 Atlas data. It's written on calendars. It's a commitment. But as we look at this timeline, as we see how the pattern of missing data and deliberate delays is accumulated, we have to ask ourselves whether that date will be kept. We have to ask whether the information will actually flow, or whether we will find more delays, more locked boxes, more classified data sets. What emerges from this timeline is not a series of isolated incidents. It's a constellation of withheld observations, delayed releases, inexplicable absences, and locked databases. We have both American and European agencies treating the same object differently from their normal procedures. We have lockbox dates that seem deliberately set far into the future. We have a spacecraft with extraordinary capabilities going silent during its most important moment. We have data releases scheduled months away when all other science typically flows within weeks. This is not randomness. This is not coincidence. This is a pattern. And patterns exist for reasons. Patterns suggest intention. They suggest coordination. They suggest that multiple organizations have decided, perhaps independently or perhaps in consultation with each other, that certain information about 3i Atlas needs to be kept from public view, at least for now. And that raises the question of what could be so important, so sensitive, so extraordinary that it would compel two major space agencies to fundamentally alter their normal procedures for transparency and data sharing. The answer might lie in what the object actually is. Part 6. The Lost Windows Mars Assets. When 3i Atlas passed close to Mars in early October, it wasn't only observed by the ExoMars Trace Gas Orbiter. There were other spacecraft in Martian orbit with cameras pointed at the sky. The Mars Reconnaissance Orbiter, which carries a camera called HERES-1 of the most powerful imaging systems we have ever put in space, had the opportunity to observe this interstellar visitor. HERES-1 is capable of pixel sizes of roughly 30 centimeters from Mars orbit. It can capture detail that would astound you. It can photograph dust storms on Mars with precision that reveals individual wind patterns. It can see rocks the size of a car from thousands of kilometers away. Given the right viewing geometry, HERES-1 could have captured unprecedented detail of 3i Atlas. It could have photographed the nucleus of the object. It could have shown structural features. It could have revealed whether the object has a simple rounded shape like a natural comet, or whether it has something more complex, more geometric, more artificial looking. But where are those images? Have you seen any high-resolution, high-REC photographs of 3i Atlas? Have they been released to the public? Have they appeared in any scientific database? As of now, the answer is no. The images have not materialized. The data has not flowed. To the researchers who requested it, if HERES-1 captured observations, those observations have been kept from public view, just like Psyche's data, just like the full ESA dataset, just like the high-resolution imagery we might expect from a camera system like that. The history of Mars Reconnaissance Orbiter and HERES-1 is a history of transparency. The camera has been returning images to Earth for nearly 20 years. Photographs of Mars surface features are released regularly. The camera has also captured imagery of other solar system bodies. When the moons Phobos and Deimos pass in front of the camera, we see those images. When comets pass through the Martian system, we have seen photographs. The default is to release. The standard is to share. Yet, when it comes to 3i Atlas, when the object came close to Mars, when HERES-1 had the perfect opportunity to capture detail we had never seen before, the data simply did not follow the normal path. Why would that be? One explanation is technical, perhaps. The camera was slated for Mars surface observations during that particular window. Perhaps the point-in priorities of the mission meant that other targets were deemed more important. Perhaps there were processing delays in downloading and transmitting the data. These are all plausible explanations. They're all things that could legitimately delay the public release of an observation, but none of them require the data to be completely absent from the archives. None of them require absolute silence. Normally, when there is a processing delay, the data portal shows that it is being processed. There is a status, there is information about when the data might become available. But consider another possibility. What if Psyche did observe 3i Atlas? What if it captured high-resolution images that showed something unexpected? What if the camera revealed structural features on the object that surprised the researchers? What if the data suggested that 3i Atlas was not simply a comet, but something else? Something with properties that demanded further investigation and internal review before any public release. In that scenario, the data would be held back. It would be analyzed carefully. It would pass through multiple levels of scrutiny, and it might be classified, at least temporarily, until decisions could be made about what to tell the public and how to tell it. The absence of Psyche imagery combined with the absence of Psyche imagery combined with the delayed ESA data creates a picture of systematic data withholding across multiple instruments and multiple agencies. We are no longer talking about one spacecraft going dark. We're talking about a coordinated pattern where every major high-resolution observation opportunity involving 3i Atlas has resulted in either missing data or delayed data. That is not coincidence. That is a decision made at a level above. Individual mission control rooms. Consider what a higher resolution image would show that a spectrum cannot. A spectrum tells us about composition, about the elements present in the object's atmosphere. It tells us what is there. But an image tells us shape. It tells us structure. It tells us whether the object has natural rounded features or whether it has edges, angles, geometric forms. It tells us whether we are looking at a natural body shaped by gravitational forces and collision history, or whether we are looking at something built, something constructed, something designed. That is the information that would be most dangerous to release, because that is the information that would force a conversation that the agencies might not be prepared to have. And so the images are kept back. The high-resolution views remain locked away and the mystery deepens. Part 7. Plasma propulsion or shield. What if 3i Atlas is not a comet at all, but a machine? What if it is a probe of some kind, a vessel designed to travel through interstellar space, and what we have been observing in its behavior are not natural physical phenomena, but the signatures of active propulsion or active systems? The idea might sound like science fiction, but let us follow the evidence and see where it leads. Community researchers who have been closely analyzing the available data have described a peculiar halo around 3i Atlas. They call it space. Invader-shaped, a reference to the pixelated alien in the vintage video game. The halo is visible in certain wavelengths of light. It surrounds the object. It is not a natural coma of dust and gas that you would expect from a comet. It has structure, it has a shape, it has edges that seem almost deliberate in their geometry. Is this the signature of a natural interaction between the object and the solar wind? The stream of charged particles flowing outward from the sun. That is the mainstream explanation. Solar wind pressure on dust and charged particles would create a halo. Natural plasma distortion could produce apparent structure. These explanations are plausible within conventional physics, but consider an alternative. What if the halo is not a distortion but an emission? What if 3I Atlas is actively generating a plasma field? What if the object is using electromagnetic shielding? Or is venting ionized material as a byproduct of some active system? A spacecraft using plasma propulsion or maintaining a magnetic shield or dumping excess heat through ionized gas would create exactly this kind of signature. The direction of the jets, the composition, the structure of the halo of it could fit a model where 3I Atlas is not a passive comet being shaped by external forces, but an active machine maintaining its own environmental bubble around itself. The parallel to another interstellar visitor is hard to ignore. In 2017, an object called Oumuamua entered our solar system and astounded astronomers. It displayed non-gravitational acceleration. That means it was speeding up in ways that could not be explained by gravity alone. It also had an unusual shape, something like a cigar or a flat rectangle. The scientific community struggled with explanations. Some proposed natural mechanisms. Some ventured that perhaps it was a solar sail, a spacecraft design that uses light pressure to accelerate. The conversations were heated and not always civil, but the possibility had been raised. The idea that an interstellar object might be something other than a natural comet had been spoken aloud. Now we have 3I Atlas with its sunward jet, its unusual composition, its geometric halo, its anomalous acceleration. And the situation is more intriguing because we have actual photographs and spectroscopy, not just indirect evidence. We have data that shows the object is behaving in ways that natural comets should not behave. The mainstream astronomical community still argues for natural explanations. They point to carbon dioxide, ice lines, and unusual nuclear compositions. They cite examples of bizarre comet behavior in Earth's own solar system. They maintain that we should not invoke extraordinary explanations when ordinary ones might suffice. This is good science. It is cautious and appropriate. But what if the ordinary explanations are insufficient? What if the data genuinely do not fit the natural models? What if 3I Atlas is anomalous in ways that force us to at least consider the possibility that we are looking at something constructed? Imagine a solar sail probe, a vessel designed to travel between stars using radiation pressure as its fuel source. Such a device would orient itself toward the sun. It would use solar energy. It would need to adjust its orientation to maintain course. The jets we observe, the halo effect, the asymmetry in the object's behavioral of it could be explained by a spacecraft maintaining its position and stability as it approached the sun for a close pass, using our star as a power source. And a navigational reference. It is speculative, yes. It is beyond the mainstream scientific consensus, certainly. But it is consistent with the observations. It is not falsified by the data. It merely requires a different set of assumptions about what the object is. And that brings us back to the silence. If researchers in government space agencies had contemplated even the possibility that 3I Atlas might be artificial, might be a probe, might be constructed rather than natural, would they not immediately classify all of the data? Would they not bring in higher-level officials? Would they not initiate internal security reviews? Part 8. The Industrial Alloy Mystery. The spectroscopic data returned from observatories studying 3I Atlas presents a puzzle that does not fit neatly into our textbooks on comet composition. Astronomers detected nickel in the out from this object, which by itself is not entirely shocking. But here's where the anomaly crystallizes. They found nickel without measurable iron in the same measurements. This is unusual. It is, in fact, deeply unusual. On Earth and throughout our known solar system, nickel and iron appear together with remarkable consistency. Their companion elements in meteorites, in asteroids, and in the cores of rocky bodies that formed alongside our planet. The ratio between them tells a story written into the cosmic dust of planetary formation. Yet 3I Atlas seems to have rewritten that story, or at least refused to follow the script we all expected. Consider the metallurgical context for a moment. Here on Earth, we have learned how to separate nickel from iron through industrial processes like the nickel-carbonyl refining technique. When humanity needs pure nickel metal divorced from iron, we have invented ways to achieve that separation. Moreover, we have engineered high-nickel alloys, materials with names like Inconel, that combine nickel with other elements to create substances that can withstand extreme conditions. These alloys are designed deliberately. They are crafted for specific purposes: durability in harsh environments, resistance to corrosion, the ability to function near intense heat sources like the sun itself. No natural process, we understand, routinely produces such refined metallurgical compositions in space. Yet here, in the outgassing from an object approaching our star, we find this signature. The JWST satellite, which has been observing 3I Atlas with its extraordinary infrared sensitivity, returned another piece of the puzzle: the coma surrounding. This object is dominated by carbon dioxide ice. This is significant because it suggests the object formed under conditions radically different from typical solar system comets. Most comets forming in the outer regions of planetary systems carry signatures of water, ice, and volatiles associated with the familiar cold zones we understand. But a carbon dioxide-rich nucleus speaks to formation near what astronomers call the carbon dioxide ice liner region, where conditions favor this specific chemistry. The question becomes inescapable: what object follows such an unusual compositional recipe? We must here inject a necessary note of scientific caution, because the temptation toward extraordinary conclusions must be balanced against the reality that nature sometimes produces weird ratios without requiring exotic explanations. A single anomalous reading, even a careful one, does not automatically prove the intervention of technology or design. Natural processes can be stranger than we anticipate. Solar heating, unusual formation histories, even chance combinations of stellar dust and volatile compounds might account for these signatures. The scientific method demands that we remain skeptical, even when the data seems to point somewhere extraordinary. Yet consider an analogy that might clarify why this matters. Imagine you're sifting through a pile of meteorites, fragments fallen from space, all bearing the expected mineral signatures of natural formation. Then you find a chunk of metal that bears the unmistakable characteristics of spaceship-grade alloy, the kind of high nickel composite that only forms under industrial conditions. You would immediately ask a different set of questions. You would want to know why it was there, where it came from, and whether it truly belonged among the natural stones surrounding it. The discovery itself does not demand that you conclude artificiality, but it demands that you investigate with renewed intensity. If 3I Atlas's composition truly does deviate from known natural materials, then both the Psyche spacecraft and other observatories would logically treat the data differently. Special review protocols might activate. Scientific committees might convene. The object might receive a classification that separates it from routine cometary observations. This is not conspiracy thinking. This is institutional procedure. When something does not fit the expected categories, institutions designed to enforce standards begin to scrutinize more carefully. The blind spot becomes critical here. If the object is indeed of exotic composition, then the silence surrounding Psyche's missing window takes on new weight. It suggests not careless delay, but deliberate gatekeeping. It raises the question that will carry us forward. Might someone be blocking the data because what is inside 3I Atlas is simply too unexpected to process through normal channels? Part 9. Coordinated censorship. The notion that multiple space agencies might coordinate to suppress or delay data about 3I Atlas sounds, at first hearing, like the architecture of paranoia. It conjures images of backroom deals, shadowy committees, and whispered memos in windowless offices. And yet, when you stop reacting to the surface and instead examine the timeline with patience, something subtler and far more troubling begins to emerge: patterns of the language of intelligence, whether human or machine, and the patterns surrounding this object is becoming increasingly difficult to dismiss as mere coincidence. NASA and the European Space Agency operate under different governments, different funding models, different institutional cultures. One answers to Washington, the other to a coalition of European nations that often struggle to agree on budget allocations, let alone on policy. In theory, these two organizations should diverge in method and response. And yet, as we move through the timeline of 3I Atlas, we see their actions converging not in lockstep conspiracy, but in a shared choreography of hesitation, suppression, and delay. It is as though separate orchestras playing different pieces in different concert halls all struck the same note at the same time. History is our guide here, and history is rarely kind to the idea that governments and agencies tell us everything. During the Galileo mission in the 1990s, the spacecraft sent back images of Jupiter's moons, images so astonishing that they threatened to overturn assumptions about those frozen worlds. Some of that data was delayed, carefully filtered, parceled out in a trickle. The Apollo program, hailed as humanity's giant leap, generated hours of audio and telemetry that sat locked away for decades before entering the public record. In the Cold War, entire classes of reconnaissance satellites operated in orbit, photographing Earth with technologies so advanced that it dwarfed civilian astronomy. The public never knew these machines existed until leaks and declassification decades later. The pattern is clear. Certain categories of data receive special handling, not because they lack scientific value, but precisely because they carry too much of it. The frameworks that explain this behavior are neither mysterious nor exotic. The first is national security. If 3I Atlas proves to be more than a comet, if it carries implications for planetary defense, sovereignty of space, or even technological parity with an unknown intelligence, then immediate disclosure would not be the default. It would trigger protocols, layers of review, and interagency deliberations. Planetary protection offers a second framework. Scientists have a duty to consider potential hazards, whether biological or material. If an object suggests even the faintest possibility of risk, agencies err on the side of silence until risk assessments are complete. A third framework is international coordination. When multiple nations investigate the same phenomenon, embargoes and controlled releases prevent chaos. The goal is not secrecy, but consistency, though to the public, the effect looks indistinguishable from suppression. Finally, there are commercial and mission priority motives. When billions are spent on spacecraft like Psyche or ExoMars, the teams that built the instruments often expect a window of proprietary access to their data. That access can stretch from months to years, creating natural silences that overlap with critical moments of discovery. All of this could be innocent. And yet, here is the uncomfortable truth. NASA has historically been remarkably open with cometary data. The Hubble Space Telescope has photographed comets countless times, and those images entered public archives with only modest delay. The James Webb Space Telescope, despite its staggering sensitivity, has revealed its discoveries to the public in a matter of weeks. Rosetta, orbiting comet 67P, sent down images in near real time, almost as if inviting the world to participate. In the discovery process, comets, in other words, have not traditionally triggered secrecy. They have been shared, dissected, published, displayed. So why does 3I Atlas break the pattern? Why is this particular visitor treated differently with silences where there should be floods of imagery? The timeline is our evidence, and its coincidences verge on choreography. In early September, Psyche experiences its missing window, a blackout that leaves unexplained gaps in its data stream. Days later, the European Space Agency's ExoMars data release stumbles on a bizarre 2099 placeholder datan error that becomes an excuse for a blanket delay, pushing the release all the way to April of 2026. At the very moment this interstellar visitor begins its most crucial phase, the data pipelines that could illuminate its behavior go dark. Meanwhile, HiRIC on Mars, the instrument capable of breathtakingly sharp images, sits on data pending release. No denial, no explanation, just silence. Part 10. The Sun Machine Hypothesis. All the threads now converge into one haunting question. The question that has lingered unspoken in the margins of every anomaly. Every missing dataset, every whispered hesitation from the institutions entrusted with telling us the truth. What if 3I Atlas is not simply a comet? Not merely an inert shard of frozen debris wandering aimlessly across the void, but instead something far more deliberate. What if it is a probe, a machine, a construct of intelligence harvesting the energy of our star for its own propulsion or operation? At first glance, such a proposal may seem audacious, even reckless. It brushes close to the boundary of science fiction, invoking images of alien technology in a field where scientists prefer the comfort of natural explanations. And yet, boldness is not the same as error. The reason this hypothesis deserves serious consideration is not that it has been proven, but that it gathers the fragments of anomaly into a pattern that conventional frameworks cannot. Like a key fitting into a lock, the artificial probe hypothesis explains more with fewer assumptions where naturalistic explanations must grow ever more strained to cover the widening gaps. The starting point is simple, undeniable, and captured in a single image. The sunward jet, the photograph from October 16th, released with clinical precision but received with mounting unease, depicts a stream of material erupting not away from the sun as physics demands, but toward it. For a comet, this is heresy. The thermodynamics of sublimation dictate that when solar radiation heats the volatile ethers buried in a comet's crust, gases erupt outward, expanding in the vacuum, carried by momentum away from the star. Cometary tales point outwarder via ballet choreographed by heat, pressure, and radiation. But here, in 3i Atlas, we see defiance. A plume directed sunward. A comet that breathes against the wind. Taken as a natural event, it is baffling. Taken as the byproduct of propulsion, it becomes intelligible. Imagine thrusters venting material in controlled bursts. Imagine a spacecraft using exhaust or energy ejection to adjust trajectory, correcting its course as it enters perihelion. Suddenly, the physics align. The anomaly becomes a maneuver. The inexplicable becomes coherent. Layer this against the backdrop of other oddities, and the picture sharpens further. The nickel-rich composition revealed in spectral analyses raises eyebrows. In nature, nickel often appears entwined with iron. In the violent crucibles of stars, to separate the two requires energy, metallurgy, a process not unlike industrial refinement. Why would a random interstellar body show such composition unless it had been processed? Unless perhaps it is less a fragment of stellar collapse and more a fragment of engineering. Then comes the detection of carbon dioxide in quantities inconsistent with ordinary cometary models. Again, chemistry can produce surprises, but the concentration and ratios here suggest something manipulated, not merely inherited from a random cloud of interstellar dust. The Psyche probe, positioned at precisely the right moment and vantage to capture clarifying imagery, suffered a curious blackout, a missing data stream, officially unexplained but conspicuously timed. Coincidence or choreography? Individually, none of these phenomena prove design, but together they resonate. Each element becomes less like a quirk and more like a puzzle piece in a larger design, converging on the outline of something that fits only when we admit the possibility of technology. The analogy to our own work is unavoidable. Consider the concept of solar sail spacecraft driven not by chemical fuel but by the pressure of photons streaming from stars. This is no longer speculation. NASA has funded studies, prototypes have flown, and entire research communities explore the mechanics of this propulsion. If humanity, barely fledgling on the cosmic stage, has already embraced this idea, why would we imagine it impossible that another intelligence, older, more advanced, far more patient, might deploy such methods on interstellar scales. Now, stretch the analogy further. Physicists have long speculated about Dyson Swarm's vast clouds of structures harvesting stellar output for energy, orbiting stars like industrial halos. What if 3i Atlas is a fragment of such infrastructure, a probe, a scout, a component designed to report back, to measure, to evaluate? Or perhaps it is something simpler, almost benign in its function. A ship ejecting excess heat, a machine discarding waste materials sunward to maintain thermal equilibrium. The plume we see as impossible might simply be routine maintenance for a vessel operating far beyond our comprehension. Skeptics, of course, push back, and their voices must be heard. Astronomers with decades of experience remind us that comets are capricious, outgassing is chaotic. Jets can erupt in strange orientations, rotational dynamics can twist plumes in unexpected ways. To leap from anomaly to technology, they argue, risks overreach. It risks pattern seeking where randomness suffices. Publications urge patience. They warn against letting our hunger for meaning distort data into narratives of alien probes. This caution is wise. Skepticism protects science from collapsing into fantasy. And yet, skepticism, if wielded too bluntly, becomes its own dogma. It blinds as surely as credulity does. To wave away anomalies with endless appeals to natural oddity is no less ideological than to leap to the conclusion of technology. The responsibility lies in balance to respect the expertise of astronomers, while also remembering that history's great leaps in science came when someone dared to say, our framework no longer explains what we see. Copernicus reimagined the heavens, not because he wanted to be audacious, but because the Ptolemaic system no longer fit. Darwin dared to say species evolved, not because he craved controversy, but because accumulated anomalies in natural history demanded a new narrative. Science advances when we admit the inadequacy of old categories. And now, with 3i Atlas, we may stand at a similar threshold. Three possibilities crystallize. The first, 3i Atlas is a natural body, an eccentric comet whose peculiarities still fit within the bounds of physics, however strained our explanations become. The second, it is a probe, a machine, the artifact of intelligence, whether ours, seeded from the deep past, or another civilization's emissary. The third, it is something liminal, an entity straddling the boundary, a hybrid system where natural processes and technological intent blur together in ways we cannot yet grasp. If it is natural, we learn humility, expanding the boundaries of cometary science to accommodate phenomena we did not anticipate. If it is artificial, the implications are seismic. It would mean that technology capable of interstellar travel exists and is already brushed against us. It would mean that the silence of the cosmos is not silence at all, but that we have been too unprepared, too unimaginative, too institutionally cautious to recognize the signals when they arrive. The final possibility, the hybrid, may be most unsettling of all. Advanced technology might look indistinguishable from geology. Machines operating on principles we barely glimpse may mimic comets or asteroids so closely that our categories collapse. 3i Atlas might not be an intruder disguised as a comet, but rather a comet that has been adapted, engineered, co-opted into service. The natural body and the artificial system might coexist, making our distinction meaningless. And here the human dimension intrudes. If such possibilities exist, what would our institutions do with them? Would they proclaim the discovery, rewriting history in a moment? Or would they retreat into silence, fearful of destabilization, of social upheaval, of losing control over the narrative? We have already seen the hints, the blackout of Psyche, the silence from agencies that should be loudest. The precedent suggests that extraordinary data, rather than being trumpeted, is quarantined. It is locked behind the closed doors of committees and bureaucracies, while the public is fed the safest story of icy debris and wayward comets. This is why the artificial probe hypothesis must be entertained, even if it unsettles. Not because we are certain, but because ignoring it risks blindness, because anomalies deserve explanations that fit, and because the silence of institutions is itself a signal. 3i Atlas challenges us to confront not only the cosmos, but ourselves, our own willingness to see what is before us and to demand transparency from the structures that claim to speak for truth. What if, in the jet streaming sunward, we are witnessing a maneuver? What if, in the metallic composition, we are seeing the trace of design? What if, in the silence of Psyche, we are hearing the echo of something too disruptive to disclose? We may never know with certainty, but if the answer is yes, if 3i Atlas is in fact a probe, a machine, a deliberate traveler through the night, then history has already turned. Humanity has already been visited, already been seen, and our only choice is whether we open our eyes to recognize it or remain comforted by the fiction of icy debris until the stars send us another messenger. Part 11. Europa Clipper's imminent window. 3i Atlas cuts its blazing trajectory toward the sun and then outward into the void. Another spacecraft, far from Earth, circles toward its own destiny. NASA's Europa Clipper mission, the centerpiece of astrobiology in this decade, has entered a moment that is impossible to ignore. It is no longer a far-off plan, a dream to test the ocean beneath Europa's frozen crust. Its critical window has arrived. In late October of 2025, Europa Clipper positions itself for its defining encounters, carrying with it the most advanced suite of instruments humanity has ever aimed at a distant moon. Its stated goal is awe-inspiring, yet simple: to answer whether life could exist in the ice-shrouded seas of Europa. But as we have learned time and again, missions are rarely confined to their official mandates. The hardware cares little for intention. Instruments designed to peer through the frozen ice of a Jovian moon are still instruments. They bend signals, capture photons, register anomalies, and in the deep and unmonitored corridors of space, intention can shift. Europa Clipper's radar system, designed to drill invisibly through ice, could just as easily be turned outward. Its higher resolution imaging arrays, expected to capture Europa's surface in astonishing detail, could be redirected to survey the heavens. Its sensors, finely tuned to identify composition, could be aimed at passing objects streaking into or out of the solar system. And here lies the heart of the matter. The spacecraft, publicly branded as a mission for astrobiology, is simultaneously a vantage point. From Jupiter's domain, Europa Clipper has a line of sight across regions of the solar system invisible to Earth-based telescopes. It occupies a perch perfectly suited for observing an interstellar traveler like 3I Atlas. Should institutional hands choose to redirect its gaze, this possibility transforms Europa Clipper from a simple exploration mission into something larger, more unsettling, and far more consequential. The analogy is direct, even brutal. A defense radar built to shield a nation from incoming missiles doubles as a tool of surveillance. A weather satellite launched to track cloud systems captures images of strategic military installations. The infrastructure of observation is promiscuous. It does not discriminate. Once constructed, it can be used for purposes far beyond its original justification. Europa Clipper is no exception. The question then presses forward. Will it be used this way? Already we know what happens when anomalous visitors enter the solar system. The case of 3I Atlas is instructive. Observations exist, yes, but institutions close ranks. The most provocative data vanish into silence or emerge only after delay. NASA's Psyche mission should have offered images of the interstellar traveler in September. Yet its feed went dark weeks before the government shut down. Coincidence or choreography, the pattern suggests more than budgetary happenstance. It suggests a controlled narrative. Now, as Clipper enters its critical phase, are we witnessing the setup for the next act in this ongoing performance? Transparency, after all, is not guaranteed. When Cassini approached Saturn's icy moon Enceladus, its instruments detected plumes of water erupting from the surface, a revelation that rewrote planetary science and expanded our concept of habitable environments. Yet, the release of that data was not immediate. The raw findings passed first through committees, institutional filters, interpretive layers. The geysers reached the public, but carefully, cautiously, and only after weeks of internal debate. That was for a discovery involving water vapor, a phenomenon still squarely within the realm of natural science. What if the stakes had been higher? What if the data had hinted not at subsurfaced oceans, but at an engineered object, a technological artifact, something carrying implications of intelligence? Would the data have seen daylight at all? Or would Cassini's findings have been sequestered into classified files, folded into the hidden corridors of government rather than the open stage of science? This is the precedent that shadows Europa Clipper. Its official task is noble, even transcendent, to ask whether life exists beyond Earth. But its position, its instruments, its timing intersect too neatly with the mysteries surrounding 3I Atlas, and because of that, the question of transparency becomes acute. Will Europa Clipper's instruments be allowed to notice what they notice? Will its data streams be shared openly, or will they be filtered, redacted? Another example of the same institutional gatekeeping we have already seen with Psyche. Space has no boundaries. There is no jurisdiction that says Europa Clipper must only observe Europa. The instruments will detect signals from whatever falls within their range. The decision lies not with the hardware, but with those who manage the flow of information. Do they tell us what the spacecraft sees, or do they decide what is too destabilizing, too dangerous, too paradigm-shifting to reveal? Consider the timing. As 3I Atlas loops around the Sun, radiating anomalies that defy explanation, Clipper positions itself for its first critical encounters. Two narratives converge, one of interstellar visitation, one of planetary science. And in the overlap between them lies a possibility institutions are unlikely to discuss openly. That Europa Clipper could witness something, perhaps even extraordinary, and that what it observes could vanish into the same silence that has followed. 3i Atlas from the moment of its discovery. The public narrative will remain simple. Europa Clipper is here to study ice, oceans, and the possibility of microbial life. Press releases will highlight stunning images of Europa's ridges and fissures. Findings will focus on chemistry, geology, and the tantalizing signatures of habitability. But behind this polished surface, the spacecraft is something more. A sentinel at the outer edge of the solar system, equipped with tools powerful enough to register anomalies and stationed at a vantage point, unmatched by any other active mission. This duality is not conspiracy, at least not in the Hollywood sense. It is institutional logic. Build an instrument and it will be used for every purpose it can serve. Position a spacecraft and it will see more than its target. The silence is not necessarily malicious. It is procedural, bureaucratic, deeply human. Institutions protect themselves. They control narratives. They release data carefully, in curated form. But for those watching closely, for those tracking the anomalies, the unexplained jets, the disappearing feeds, the pattern becomes clear. Europa Clipper stands at the threshold of that pattern. Will it reinforce the silence, or will it break it? The stakes extend beyond science. They reach into politics, security, even philosophy. If Europa Clipper were to register something unusual, a trajectory like 3i Atlas, a signal inconsistent with natural behavior, what happens next? Does the data flow instantly to public servers, or is it quarantined? Are the scientists aboard allowed to speak freely, or are they bound by non-disclosure under the guise of further analysis? Does a discovery become a moment of collective wonder, or is it sequestered into institutional vaults until it can be managed? We do not yet know. What we do know is that the convergence of timing, instruments, and positioning makes Europa Clipper impossible to ignore. It is not simply a mission to Europa. It is the next node in a growing surveillance network, a silent witness to the cosmic traffic flowing through the solar system. And as 3i Atlas blazes past the sun, Europa Clipper orbits into history, carrying with it the chance or the danger of becoming the next chapter in a story we're only beginning to glimpse. The universe has no obligation to reveal its secrets neatly. One mission at a time. Discoveries arrive unexpectedly on the edges of frames, in anomalies not predicted by proposals or budgets. Europa Clipper may discover life beneath ice, or it may detect something else entirely. Something that forces us to rethink what we know. About visitors like 3i Atlas, the choice, as always, will not be in the instruments. It will be in the silence that follows. Part 12. Hera Mission Planetary Defense or Planetary Surveillance. The European Space Agency has announced ambitious plans for a mission designated Hera, scheduled for deployment in 2026, but already by late 2025, the preparations are accelerating, both in the laboratories that build its instruments and in the institutional corridors where priorities are quietly recalibrated. The official explanation is simple enough. Hera is a planetary defense mission. Its stated task is to rendezvous with the Didymus binary asteroid system, the very same system that NASA's DART spacecraft targeted in 2022 when it slammed into the smaller moonlet Dimorphos in the first real demonstration of a kinetic impact deflection. The purpose of Hera is to measure what happened by charting Dimorphos's new orbit with exquisite precision. Hera will quantify how much of a nudge the impact delivered and, by extension, how effective such interventions might be if Earth were ever threatened by an incoming asteroid. On the surface, the goal is clear, benign, and uncontroversial. Measure the aftermath of an experiment designed to protect our planet. And to be fair, that justification is compelling. Earth lives in a shooting gallery. Throughout geological history, our world has been bombarded by rocks and ice from space, some of them large enough to reshape climates, devastate ecosystems, and reset the evolutionary clock. The Chicxulub impact, 66 million years ago, ended the age of dinosaurs and opened the ecological niches that eventually allowed mammals and us to flourish. That single event remains a sobering reminder that planetary impacts are not rare geological curiosities, but existential threats. In that sense, the billions invested in developing planetary defense strategies are a kind of cosmic insurance policy. If we can detect threats early enough and deflect them with precision, humanity buys itself a margin of safety against a universe that is indifferent to our survival. Yet, as is often the case with ambitious space missions, the stated purpose is only part of the story. What Hera represents, once one looks past the polished press releases, is something more complex and arguably more troubling. The spacecraft's instruments are designed with extraordinary sensitivity. Its radar systems, optical images, and laser sensors are tuned to detect tiny fragments, subtle shifts in trajectories, and delicate surface features on objects millions of kilometers away. That same sensitivity, however, does not turn off once. The spacecraft leaves Didymus behind. The same radar that maps an asteroid's rubble pile can also be directed elsewhere. The same cameras that characterize surface boulders can just as easily monitor unusual objects passing through interplanetary space. In this sense, Hera embodies the dual-use principle that has always haunted technology. Every defensive system, by its nature, is also a surveillance system. A radar designed to detect incoming missiles also tracks civilian aircraft. A weather satellite launched to study storms inevitably photographs military installations, power plants, and troop movements. A telescope meant to study planetary defense doubles as an instrument to observe anything entering the inner solar system, whether ordinary or anomalous. The dually used character is not accidental. It is the structural feature of technology itself. Once you build the capacity to monitor for threats, you automatically inherit the ability to monitor for everything else. The troubling analogy is that of missile defense. When nations built early warning radars, the justification was always couched in survival. If we detect an incoming strike, we can respond before annihilation. Yet once those radar domes and satellites were operational, they inevitably expanded their role into broader surveillance networks, monitoring not just nuclear missiles, but atmospheric tests, rocket launches, even orbital debris. The infrastructure expanded quietly, step by step, and public discourse never quite caught up to the reality. Hera is poised to follow a similar trajectory. It is framed for the public as planetary defense, but its actual function extends into a more shadow domain. It becomes, whether explicitly acknowledged or not, a surveillance platform for interstellar anomalies. It becomes a sentinel against visitors like 3i Atlas. And this is where the context sharpens into focus. In the last several years, since Oumuamua and then 3i Atlas, the scientific community has been forced to confront objects that do not fit neatly into the categories of asteroid or comet. They accelerate in strange ways. They display unusual spectroscopic signatures. They produce anomalous jets from unexpected regions. And most troubling of all, institutions tasked with monitoring them have shown patterns of selective silence, delays in data release, or conspicuous cutoffs in transmission at the very moments the public might expect clarity. When 3i Atlas performed its Mars flyby, multiple orbiters should have captured extraordinary detail, yet only carefully curated images emerged absent of anomalies. When NASA's Psyche probe was positioned to provide potential imaging in September 2025, the feed abruptly went dark, and then only weeks later, a ground-based telescope revealed a propulsion-like jet from the front of the object, evidence that may be the strangest yet. This institutional silence sets a precedent. If the agencies already responsible for planetary science selectively gatekeep information about anomalies, what reason do we have to expect Hera will be different? Its data, like Psyche's, will flow back through official channels, filtered through institutional protocols. Its instruments, though capable of monitoring anomalies, will be reported on only within the framing of asteroid deflection. If something unexpected is detected, say, an unnatural trajectory or an unusual material signature, the most likely outcome is not immediate public disclosure, but classified review. The template has already been written by the way Oumuamua and 3i Atlas were handled. The ethical and political question is whether this dual-use nature should be openly acknowledged. When taxpayers fund a mission like Hera, they do so under the understanding that it is a planetary defense effort. Yet, what if its instruments are also quietly tasked with anomaly monitoring? Should the public not be informed that their defense mission doubles as a surveillance system for detecting interstellar visitors? Should there not be protocols debated openly about what happens if Hera detects something unambiguously artificial? The refusal to articulate these questions does not erase them. It simply pushes them into the background, leaving decisions to be made behind closed doors. This silence is not necessarily born from malice. Institutions evolve according to predictable logics. Once the ability to monitor exists, it will be used. Once data streams are flowing, they will be scrutinized. And once anomalies are discovered, protocols will be designed to manage them. What begins as planetary defense inevitably expands into planetary monitoring, then into anomaly detection, and eventually into information control. That sequence is not conspiracy. It is bureaucratic gravity. But the result is similar. The public narrative remains planetary defense, while the actual operational capability becomes something far broader. In late 2025, as 3 Atlas recedes toward the outer solar system after its dramatic perihelion passage. The timing of Hera's ramp-up feels almost symbolic. One interstellar visitor departs, another spacecraft prepares to launch, and the infrastructure for a new phase of space science takes shape. We are transitioning from an era of passive astronomy into an era of active intercession and surveillance. No longer are we content to wait for anomalies to appear in telescopes. We are building spacecraft to meet them, to measure them, to guard against them. And in doing so, we blur the line between science and security, between exploration and control. The danger is that public transparency cannot keep pace with institutional adaptation. The same agencies that chose silence during the Psyche cutoff and the Mars flyby will likely extend the same silence to Hera's data when the time comes. The public will see glossy releases about orbital deflection efficiency, about rubble pile, asteroids, about surface composition, and perhaps hidden in the background there will be anomalies, signatures, trajectories that do not fit. Those anomalies will not reach the press release. They will flow instead into classified channels, studied by committees whose deliberations never touch public forums. This is the emerging pattern of 21st century space science. It is not a conspiracy of individuals, but a structural evolution of institutions. As technologies become more powerful, their uses expand. As anomalies multiply, protocols of silence deepen. As planetary defense becomes planetary surveillance, we enter a new phase where algorithmic gatekeeping determines what the public knows about the universe. Hera, in this sense, is more than a mission. It is a symbol of this transition. On the surface, it measures the deflection of a rock. Beneath the surface, it builds the infrastructure to monitor interstellar anomalies. And behind closed doors, it prepares protocols for discoveries that may challenge our understanding of what moves through our cosmic neighborhood. The silence that followed 3i Atlas will not vanish with Hera. It will be institutionalized. And as 2025 closes with the spacecraft nearing completion, the real question we must ask is not whether Hera will fulfill its mission. It is whether we, the public, will ever be allowed to see the full extent of what it discovers. Part 13. AI in Space, Science, the Hidden Reviewer. Throughout 2025, the astronomical community has been increasingly deploying artificial intelligence, AI, and machine learning, ML, systems to process the overwhelming flood of data pouring in from space telescopes and interplanetary spacecraft. This isn't just a matter of efficiency, it's survival. Modern observatories generate more data in a single day than astronomers could manually pass in years. The James Webb Space Telescope, JWST, alone produces terabytes of raw imagery and spectroscopy. Every 24 hours, add contributions from Hubble, Chandra, TESS, Gaia, ground-based surveys like Vera Rubin, and planetary spacecraft such as Psyche, Europa Clipper, and the Mars orbiters, and the fire hose becomes unmanageable. So astronomers leaned into automation. AI is now the first set of eyes on most cosmic data, acting as a filter, organizer, and triage nurse before a human researcher ever logs in. What might once have been uploaded wholesale into open archives now travels through algorithmic sieves, trained models that decide what looks normal and what looks anomalous. At first glance, this seems rational. Without automated classification, data archives would drown researchers in noise. But as with every filter, the danger isn't in what gets through. The danger lies in what doesn't. Here's the threshold that has received almost no public attention. When AI becomes responsible for the first pass at categorizing data, it inherits enormous power over what humans ultimately see. Every system is built with assumptions. Algorithms are trained on examples of normal and expected signals. When an observation fits those expectations, it flows smoothly into the public archive. When it doesn't, the system doesn't throw it out. It does something subtler. It raises a flag. If the anomaly looks like instrument noise, the system may label it as error. If it looks like a deviation from a known pattern, it routes it into a review pipeline. If it is too extreme, it may be locked into indefinite pending verification status. This means a telescope can capture extraordinary physics. But whether the world ever sees it depends on whether the anomaly passes both algorithmic and human gatekeepers. In fairness, anomaly detection isn't sinistered by design. In fact, it's essential. In medical imaging, AI highlights strange growths in an MRI that a radiologist might miss. In cybersecurity, anomaly detection flags unusual network activity before a breach escalates. In astronomy, it keeps corrupt pixels, cosmic rays, and telemetry glitches from being mistaken for exoplanets or supernova. Without this, science would drown in false positives. But here's the paradox. What happens when the anomaly isn't noise, but genuine novelty? What happens when the very phenomenon we want to discover looks like error to an algorithm trained on the past? Now, apply this architecture to 3I Atlas, the third known interstellar object to pass through our solar system, and perhaps the strangest yet. If NASA's Psyche probe or ESA's orbiters captured data showing a sunward jet unlike conventional sublimation, a nickel-rich composition with absent iron, or non-gravitational accelerations too directional to be explained by our outgassing, every one of those features would have triggered anomaly protocols from the AI's perspective. These data points don't fit any cometary training set, so the system would automatically flag them as suspicious, routing them away from the bulk stream and into controlled review. Notice this requires no conspiracy. It's just the system doing its job, but once flagged, institutional discretion takes over. Humans decide, do we release it immediately? Do we hold it for extended analysis? Do we quietly delay or bury it? The silence in Psyche's data archive between September 1st and 5th, the very days it should have imaged. 3 Atlas now looks less like a glitch and more like the signature of a data pathway diverted into quarantine. The common thread: anomalies enter limbo, not rejected, not confirmed, but stuck in a zone where gatekeepers have infinite discretion. Now imagine applying that same structure to astrophysics, where the anomaly might represent not a tumor or a cyber attack, but the first signature of non-human technology in interstellar space. There's a deeper danger. The training datasets used to calibrate these AI filters are built on assumptions of normality. Comet spectra are modeled on ice, silicates, and organics. Orbital dynamics are modeled on Newtonian and post-Newtonian mechanics. Jets are modeled on sublimation physics. But if nature or engineering delivers something outside those parameters, the algorithm doesn't know how to handle it. It only knows this is off script. Thus, the more powerful our anomaly filters become, the more they risk turning into novelty suppression engines. What gets caught may not be noise. It may be the frontier of discovery. On top, the institutional psychology, agencies like NASA and ESA operate under enormous political pressure. Their reputations hinge on avoiding embarrassment, data releases that appeared a strange risk, ridicule, misinterpretation, or sensational headlines. This creates a system where the riskiest data, the very anomalies that might redefine physics, are the least likely to see daylight. This brings us back to Psyche. Officially, Psyche's raw image archive shows no files between September 1st and 5th. The feed resumes September 8th with nothing to explain the blackout. If an algorithm flagged 3 Atlas observations during that time, the data may have been routed into internal review pipelines. From there, human committees may have chosen to hold it, whether out of caution, fear of error, or fear of what? It implied, we cannot know. What we do know, the gap is real. The missing days coincide precisely with the window when Psyche should have captured the most revealing close-approach images of 3I Atlas. And the silence since has been absolute. This is bigger than Psyche. What we've seen is the first public symptom of a deeper structural change. Astronomy in 2025 doesn't work like astronomy in 2005. Back then, data pipelines were simpler. Telescopes uploaded raw files, researchers combed through them, anomalies. And all today, AI filters decide first what looks normal, what gets flagged, and what gets rerouted. The filtering is more sophisticated, the gatekeeping more automated, and the transparency less visible. The infrastructure of discovery has become, without debate, an infrastructure of control. Ironically, this transformation was driven by real need. The data deluge is genuine. Without filters, the system would collapse under its own weight. But in solving one problem, we created another. A system where the novelty threshold is lower than reality itself. When an interstellar object, like 3I Atlas, does something bizarre against expectation, emits Nicorich jets, resists gravitational modeling, the system doesn't celebrate. It quarantines, and so the very tools meant to protect us from false positives may be ensuring we miss the most important truths of all. This isn't about one spacecraft, one comet, or one missing batch of images. It's about the future of discovery itself. If we allow anomaly filters and institutional discretion to define what science gets to see, then our picture of the cosmos will shrink to the boundaries of our expectations. We will only discover what we already know how to categorize. The history of science shows the opposite pattern. Real breakthroughs arrive as anomalies. Radioactivity was an error until it became a revolution. Quasars were radio noise until they revealed black holes. Dark matter began as a discrepancy in galactic rotation curves. Every frontier began as an anomaly someone chose to take seriously. The story of 3I Atlas forces us to ask, are we still willing to face anomalies? Or have we built a system where algorithms and committees politely remove them from view? If the latter, then a scandal is not that Psyche's images are missing. The scandal is that we designed a world where anomalies vanish by default, buried not by conspiracy, but by code. Science thrives when its rarest surprises are allowed into the light. Without that, we risk a future where telescopes see everything, but humanity learns nothing. Part 14. The New Physics Rumblings. Within the scientific literature of 2025, rumblings of genuinely novel physics have begun to surface. These aren't the usual incremental refinements, the tiny tweaks to orbital mechanics, or new coefficients plugged into long-standing equations. What's bubbling up now are hints of something more fundamental. Emerging from the frontier where interstellar objects brush against our models of solar radiation and gravity. The focal point of this tension is 3I Atlas, an interstellar interloper whose behavior seems determined to humiliate textbook cometary physics. From the first high-resolution datasets, institutions tracking 3 Atlas flagged characteristics that simply don't fit the mold. Mass estimates suggest something anomalously dense compared to its apparent size. If you take its observed brightness, surface area, and coma formation at face value, you'd predict a mass characteristic of volatile ice mixed with rocky silicates. Just another dirty snowball. But the numbers refused to line up. Instead, 3I Atlas appears far heavier than its size justifies, as if it were composed of alloys or engineered composites rather than porous ice. This discrepancy alone would be enough to keep theorists busy for a decade, yet it's only the beginning. The real scandal is the object's acceleration patterns. Ordinary comets speed up or change course due to a simple, well-understood effect, non-gravitational acceleration. As a comet nears the Sun, volatile materials inside its nucleus vaporize. The escaping gases erupt as jets, creating a gentle but continuous push, like tiny thrusters firing at random. Astronomers long ago learned to fold this phenomenon into their orbital models. It's so routine that software like JPL's Horizons can predict it without fanfare. Outgassing is why cometary trajectories wiggle compared to purely gravitational paths. It's expected, documented, and rarely controversial. But 3I Atlas is not playing by the rules. The magnitude and, more importantly, the directionality of 3I Atlas's acceleration don't match any thermal sublimation model. Instead of a chaotic, averaged-out set of microjets, we see forces that are too strong, too clean, and too aligned. Imagine watching a campfire. Sparks and smoke swirl randomly. Now imagine those sparks all shooting in perfect formation as though orchestrated by some invisible hand. That's the level of strangeness we're talking about. If you were to diagram the acceleration vectors, you'd find components that appear controlled rather than the force is not only larger than models predict, but often points in directions outgassing alone cannot justify. Mainstream theorists first reached for electrostatic forces, the solar wind, the charged particle stream that bathes every object in the inner solar system, can interact with dust clouds and generate forces beyond gas pressure. This is real physics. Comets often carry charged environments, yet calculations suggest the magnitudes required here would dwarf what solar wind typically produces. Almost like claiming a household fan can shove a truck down the street. Another idea: radiation pressure. Light itself carries momentum, and over long time scales, it can push small objects, especially if those objects are thin and reflective like a solar sail. But comets are tumbling, asymmetric, and absorptive, not mirrors designed to harness photons. The push from sunlight is real, but too weak to explain the observed accelerations, unless three artless possesses surfaces or coatings we've never encountered in nature. In other words, natural mechanisms stretch and stretch, but the fabric tears before it covers the anomalies. That leaves the idea most scientists hate to say out loud: active propulsion. What if 3i Atlas is not a passive rock, but a vessel or probe steering through the solar system with deliberate control? The sunward jet captured in Auger's imagery becomes, under this interpretation, not sublimation but thrust. Its composition: anomalous nickel cyanide complexes. Refractory materials suddenly look less like random chemistry and more like engineered design optimized for durability in irradiation environments. The analogy is simple. If you saw a car rolling uphill without its wheels touching the ground, you'd assume some hidden propulsion. Likewise, if a cosmic body accelerates in ways outgassing can't explain, you're forced to ask if something unseen is pushing it. Now, none of this means the alien probe hypothesis is confirmed. Far from it. The culture of astronomy thrives on skepticism, and rightly so. Extraordinary claims demand extraordinary evidence, and suggesting that an interstellar object is an engineered craft would represent one of the most extraordinary claims in the history of science. And so, in journals and conferences, the tone remains cautious. Authors frame their findings in passive voice, hedge their conclusions, or emphasize model uncertainties. Sky at Night magazine and other respected publications acknowledge the anomalies, but emphasize natural explanations first. It is an understandable conservatism, but here lies the danger. Caution becomes suppression when it blinds us to phenomena that truly exceed our frameworks. Skepticism morphs into dogma when it refuses to entertain the possibility that the data is exactly what it looks like. This is why the silence around NASA's Psyche probe has taken on such a sinister flavor. The spacecraft was publicly slated to image 3i Atlas around September 3rd to 4th. Yet in Psyche's raw archive, there is a blackout. Between September 1st and 5th, no images exist. The data stream resumes only on September 8th, and no official explanation bridges that gap. This is not the October government shutdown that came later on October 1st. The missing data falls outside that window, which raises the obvious question: was this an accidental lapse, a systems glitch, or a deliberate omission? If Psyche captured something profoundly anomalous during those missing days, withholding it would represent not just bureaucratic inertia, but an act of knowledge control. Imagine if the first images of microbes on Mars were quietly deleted and never discussed. The act would redefine the relationship between science and power. The Psyche blackout doesn't exist in isolation. The European Space Agency has been embroiled in its own data controversies. The ExoMars Trace Gas Orbiter initially scheduled data releases with a glitch that labeled them as embargoed until the year 2099. Embarrassing error or Freudian slip? The response was to impose a blanket delay, pushing all releases to April 3rd, 2026. Meanwhile, today's newly released ESA image captured back in August, shows a sunward jet on 3I Atlas that dovetails perfectly with the anomalous acceleration story. This retroactive disclosure feels less like transparency and more like slow drip control. And then there are still pending higher resolution datasets from higher IC on Mars. Plus, late October flyby opportunities involving Hera and the Europa Clipper. Each represents another chance to glimpse 3I Atlas up close. Each becomes another test case of whether data will flow freely or vanish into silence. If the anomalies of 3I Atlas are genuine, if the object is accelerating in ways that demand new physics or reveal hidden propulsion, then what's being suppressed is not just curiosity, but potentially the key to an entirely new domain of knowledge. Consider history. Radioactivity was once a bizarre, anomaly, phosphorescent rocks glowing in the dark. Superconductivity was a laboratory oddity, unexplained for decades. Each violated expectations until theory caught up. Each reshaped entire industries. Now imagine propulsion without fuel, spacecraft steering on light, matter engineered to survive. Near-stellar environments. If 3I Atlas embodies any of this, then the missing Psyche data represents not just a bureaucratic hiccup, but the suppression of revolutionary science. The institutions meant to expand human knowledge risk becoming its gatekeepers. By controlling data release schedules, framing anomalies as glitches, and maintaining official silence, they transform from laboratories into fortresses. This is not conspiracy theory. It's structural sociology. Large organizations instinctively protect themselves from reputational risk. The more extraordinary the data, the higher the perceived risk, the stronger the impulse to bury it. But in doing so, they suffocate the very engine of discovery. Science thrives only when anomalies are confronted. Hidden, the blackouts, delays, and embargoes suggest a shift away from confrontation toward concealment. Taken together, these facts weave a disturbing pattern. If 3I Atlas truly represents novel physics or even engineered propulsion, then we are not just failing to confront it. We are actively hiding from it. This moment feels like standing at the edge of a dark forest, hearing something vast moving among the trees, and choosing to cover your ears rather than step forward with a lantern. Caution is natural. Fear is understandable. But history shows that progress belongs to those willing to face the anomalies others dismiss. If the institutional silence continues, then the true scandal will not be whatever 3I Atlas turns out to be. The scandal will be that we looked away when the universe handed us the chance to rewrite the physics of reality itself. Part 15. Beyond Atlas, the pattern of silence. To understand 3I Atlas in its complete significance, we must zoom outward and recognize that this single object represents not an isolated anomaly in data management, but rather a thread in a much larger tapestry of silent science and withheld information throughout 2025. The pattern has become visible once you know to look for it, manifesting across multiple domains of research and technology in ways that suggest something deeper than random institutional delays or coincidental bureaucratic confusion. Consider the fusion energy research community, where experiments at facilities like ITER and various privately funded ventures have achieved breakthrough. results that should have triggered celebratory announcements and rapid publication cycles. Yet the release of detailed data has consistently lagged behind the announcements. Results are presented in summaries, while raw data remains in restricted access pending further review and validation protocols. The pattern suggests that something in these results warrants special handling before public circulation. Yet the specific nature of what requires such caution has been vaguely communicated or withheld entirely. The fusion community exists in a strange institutional space where national security considerations overlap with commercial competition, creating plausible frameworks for suppression even when the discoveries are nominally civilian science. The Chinese Fast Radio Telescope, one of the most powerful in the world, has detected ultra-fast radio bursts and gathered data about transient phenomena that would normally flow into the international astronomy community for collaborative analysis. Yet significant portions of the FAST dataset remain unavailable to researchers outside China. The justification emphasizes scientific priorities and the desire to publish first in domestic venues. But the larger effect is the same: important. Astronomical data remains sequestered, unavailable for the kind of collaborative verification and analysis that accelerates discovery. The pattern operates across geopolitical boundaries. It manifests in both Western and non-Western scientific institutions. It suggests that something systemic in how we manage cutting-edge data has shifted toward restriction. Defense, aerospace agencies have similarly kept classified vast amounts of data about spaceplanes, advanced launch systems, and orbital platforms. DARPA and related organizations maintain opaque protocols around the development and deployment of space-based assets that might observe Earth or the broader cosmos. This secrecy is justified through legitimate national security frameworks, yet its effect is to remove from public knowledge vast sectors of space, technology, and observation capability. We do not know what such systems might discover. We do not know how they might observe Three-Eye Atlas or similar phenomena. We simply understand that this capability exists, is being developed and deployed, and operates entirely outside public accountability. When you draw together these examples from fusion research, radio astronomy, and military aerospace alongside the data restrictions surrounding Three-Eye Atlas, a coherent pattern emerges that transcends any single institution or mission. We appear to be witnessing the emergence of a new norm in scientific data management, where anomalies, unexpected discoveries, and phenomena that deviate from established models receive systematic gatekeeping treatment. The mechanisms vary. Sometimes, data is simply held in restricted archives pending review. Sometimes it is processed through algorithmic filters that delay or suppress anomalous readings. Sometimes it is sequestered through national security frameworks. Sometimes it is withheld through international data embargoes designed to coordinate release timing. The specific mechanisms matter less than the convergent outcome. Access to anomalous data becomes restricted, and that restriction operates largely without public discussion or consent. The societal implications deserve direct articulation. In democracies, we have historically operated under the assumption that the public has the right to access scientific data and the right to participate in conversations about what discoveries mean for our understanding of reality. We have built institutions around transparency. We've created legal frameworks requiring open access to government-funded research. We have embraced the ideal that knowledge belongs to humanity rather than to institutional gatekeepers. Yet the pattern of silence emerging in 2025 suggests that this commitment may be eroding, replaced by a more restrictive model, where anomalies are treated as potential threats to institutional authority rather than opportunities for genuine discovery. Who gets to decide what we, the public, and the broader scientific community are allowed to see? What happens when anomalies emerge that do not fit our models? These questions grow increasingly urgent as the infrastructure for detecting and monitoring unusual phenomena expands. Europa Clipper will observe Jupiter in the coming weeks. Hera will prepare for its 2026 deployment. Countless other satellites and telescopes will continue their work, gathering data that will flow through algorithmic filters and institutional review protocols. If the pattern of silence continues unchanged, then the most significant discoveries will be the ones we never see, frames we're never allowed to examine, the data we're never given the opportunity to interpret. Return now to the beginning, to 3i Atlas and Psyche's missing window. If the silence is louder than the data, then the most important story told by this entire episode is not what we observed, but what we were prevented from observing. The greatest discovery may indeed be the one we still have not been allowed to see. As we await the next scheduled data release from Hi-Risi in April of 2026, keep your attention fixed not on the data that arrives, but on the data that does not. Watch for the gaps. Notice the delays. Observe the instances where institutions explain delays through bureaucratic processes rather than transparent scientific reasoning. The pattern of silence extending across fusion research, radio astronomy, aerospace programs, and now commentary. Observation tells a story about institutional change that happens quietly, without announcement, without democratic deliberation. It tells a story about how the systems designed to advance human understanding can transform into systems that constrain understanding when what we might understand threatens existing frameworks of authority and control. In the end, the mystery of 3i, Atlas, and Psyche's missing window may not be about the object itself, but about what we are willing to know and what we choose to suppress. The greatest discovery may not be in the data we see, but in confronting the question of why we are not allowed to see it. That question carries implications far beyond astronomy, far beyond this single object approaching the sun. It carries implications about the kind of civilization we are becoming, about whether we trust our institutions with the truth, and about whether institutions trust us with knowledge they deem too disruptive to control. These are the questions that will echo long after 3i Atlas has passed its perihelion and disappeared into the outer darkness, leaving us wondering what we missed and what we chose not to see. Part 16. The institutional reflex why silence becomes the default. When confronted with anomalies that challenge established paradigms, large scientific institutions don't typically react with immediate transparency. Instead, they follow a predictable pattern that has become increasingly visible throughout 2025. This pattern isn't necessarily born from malicious intent, but from structural imperatives that prioritize stability over revelation, control over curiosity, and institutional preservation over scientific progress. The first stage of this institutional reflex is isolation. When anomalous data first emerges, whether it's the sunward jet of 3i Atlas, unexpected nickel signatures without accompanying iron, or acceleration patterns that defy conventional physics. The initial response is to quarantine the information. This happens through multiple mechanisms. Data might be routed into special review folders rather than flowing directly to public archives. Access permissions might be restricted to a small group of internal researchers. Public statements might be carefully crafted to acknowledge the observation while downplaying its significance. The goal at this stage is containment, preventing the anomaly from triggering widespread attention before its implications can be fully assessed. The second stage is normalization through delay. Once isolated, the anomalous data undergoes a period of extended analysis that far exceeds normal review timelines. What might typically take weeks now stretches into months or even years. During this period, institutions often cite technical reasons for the delayed processing challenges, calibration requirements, peer review procedures. These explanations aren't necessarily false, but they mask a deeper reality. The data is being held until it can be framed in a way that minimizes disruption to existing paradigms. Sometimes, this involves finding conventional explanations that, while strained, might plausibly account for the anomaly. Other times, it involves waiting until public attention has shifted elsewhere, reducing the impact of eventual disclosure. The third stage is managed release. When the data finally emerges, it often does so in a carefully controlled manner. Press releases might emphasize the least controversial aspects of the findings. Technical papers might be published in specialized journals rather than hype publications. Public presentations might focus on methodology rather than implications. The result is a gradual, almost imperceptible integration of the anomalous into the scientific mainstream, so slowly that it never triggers the paradigm shift it might have provoked if released immediately and without qualification. We've seen this pattern play out repeatedly with 3I Atlas, the initial sunward jet. Observation was acknowledged but framed as an unusual but not unprecedented cometary phenomenon. The nickel-rich composition was reported but presented as a rare but natural occurrence. The acceleration anomalies were documented but attributed to complex interactions between solar, wind, and outgassing. Each finding was technically accurate but contextually minimized, preventing the collective recognition that together they pointed toward something extraordinary. The institutional reflex toward silence serves multiple functions. First, it protects organizations from reputational risk. Premature announcement of a discovery that later proves erroneous can damage credibility for years. Second, it maintains control over the narrative. By managing how and when information is released, institutions can shape public understanding and interpretation. Third, it prevents social disruption. Discoveries that challenge fundamental assumptions about humanity's place in the universe, such as confirmed evidence of extraterrestrial technology, could have profound psychological, cultural, and political consequences that institutions may feel unprepared to manage. However, these protective functions come at a cost. The same mechanisms that shield institutions from risk also shield the public from knowledge. The same control that preserves institutional stability also preserves scientific paradigms that may be outdated or incomplete. The same prevention of disruption also prevents the rapid advancement of understanding that comes from confronting anomalies. Head-on. The result is a growing gap between what institutions know and what they share. This gap isn't necessarily malicious, but it is consequential. It creates a situation where the scientific community operates with incomplete information, where public understanding lags behind institutional knowledge, and where the pace of discovery is artificially slowed by institutional caution rather than genuine scientific uncertainty. What makes this particularly troubling in the case of 3I Atlas is that we're not dealing with minor anomalies that might be easily explained away. We're confronting a pattern of evidence that, taken together, points towards something that could fundamentally reshape our understanding of the cosmos. The sunward jet, the unusual composition, the acceleration patterns, the missing data from multiple spacecraft, these aren't isolated quirks, but interconnected pieces of a puzzle that doesn't fit into our existing frameworks. If 3I Atlas were merely an unusual comet, the institutional reflex towards silence would be less concerning. But if it represents something more, if it's evidence of extraterrestrial technology, if it demonstrates physics we don't understand, if it carries implications for humanity's future in space, then the pattern of withholding and delay becomes not just cautionary, but potentially catastrophic. It means we might be missing opportunities to learn, to prepare, to respond, to understand our place in a universe that may be far more complex and populated than we've imagined. The institutional reflex towards silence is not unique to space science. We've seen similar patterns in other fields facing disruptive discoveries. In medicine, breakthrough treatments sometimes face years of additional testing and regulatory hurdles before reaching patients who could benefit immediately. In climate science, alarming findings have sometimes been downplayed or delayed to avoid public panic or political backlash. In artificial intelligence research, concerns about advanced systems have sometimes been kept quiet to prevent public misunderstanding or overreaction. What makes the space science context particularly significant is that the objects of study don't wait for our institutional processes. 3I Atlas won't pause its journey through our solar system while we decide how to handle what we're learning about it. The universe doesn't operate on our bureaucratic timelines. By the time institutions feel ready to share what they know, the opportunity for further observation, for additional data collection, for real-time analysis may have passed. This mismatch between cosmic timeframes and institutional processes creates a fundamental tension. The cosmos operates on timescales of billions of years, but presents us with fleeting opportunities to understand it. Our institutions, designed for stability and risk management, operate on timescales of budgets, elections, and career cycles. When these two temporal rhythms collide, the result is often missed opportunities and delayed understanding. The solution isn't necessarily to eliminate all institutional caution. Some level of verification and review is essential to good science. But we do need to recalibrate the balance between caution and curiosity, between stability and discovery, between institutional preservation and scientific progress. We need mechanisms that can rapidly assess and share anomalous findings without sacrificing scientific rigor. We need transparency protocols that account for the unique challenges of discoveries that might have profound implications beyond the scientific community. Most importantly, we need a cultural shift within scientific institutions, one that values the courage to confront anomalies as much as the prudence to verify them. We need to recognize that, in the quest to understand our universe, the greatest risk isn't making mistakes or facing disruptions. It's failing to see what's actually there, because we've built systems that prioritize comfort over curiosity, stability over revelation, and institutional preservation over the advancement of human knowledge. Part 17. The public's right to know in an age of cosmic discovery. The story of Three-Eye Atlas and the institutional silence surrounding it raises fundamental questions about transparency, accountability, and the public's right to know. In an era when scientific discoveries may have profound implications for humanity's future, these questions aren't merely academics. They strike at the heart of how democratic societies function when faced with knowledge that could reshape our understanding of ourselves and our place in the universe. Historically, the relationship between scientific institutions and the public has been built on an implicit contract. Public funding supports scientific research, and in return, institutions share their discoveries openly, allowing society to benefit from new knowledge and participate in conversations about its implications. This contract has been particularly strong in space science, where NASA and other agencies have traditionally emphasized public engagement, education, and transparency. Images from the Hubble Space Telescope, findings from Mars rovers, and discoveries from the James Webb Space Telescope have all been shared widely, inspiring public interest and support for space exploration. However, the case of Three-Eye Atlas suggests this contract may be fraying. When multiple space agencies simultaneously withhold or delay data about an interstellar object displaying anomalous characteristics, they violate the expectation of transparency that underpins public support for scientific research. This violation isn't necessarily malicious, but it is consequential. It creates a situation where institutions funded by the public are making decisions about what the public is allowed to know. Without public input or accountability, the ethical dimensions of this situation become particularly stark when we consider what might be at stake. If Three-Eye Atlas is merely an unusual natural object, the institutional silence represents poor scientific practice, but not necessarily a betrayal of public trust. However, if the object displays characteristics suggesting artificial origin or advanced technology, then withholding this information becomes one of the most significant ethical breaches in the history of science. Denying humanity knowledge that could fundamentally reshape our understanding of our place in the cosmos, the argument for institutional discretion typically rests on several pillars. First, there's the concern about premature release of information that might later prove incorrect. Second, there's the worry about causing public panic or social disruption. Third, there's the need to protect national security interests that might be implicated by certain discoveries. Fourth, there's the desire to maintain scientific credibility by ensuring all findings are thoroughly verified before publication. While these concerns have some merit, they must be balanced against the ethical imperative of transparency. In democratic societies, the default position should be openness, with restrictions applied only when absolutely necessary and for limited periods. The burden of proof should be on those who advocate for secrecy, not on those who demand transparency. Moreover, any restrictions should be subject to independent oversight and regular review to prevent them from becoming permanent. The practical implications of institutional silence extend beyond ethical considerations to the very progress of science itself. When data is withheld, it prevents researchers outside the privileged circles from contributing their expertise to understanding anomalies. The collective intelligence of the global scientific community is one of our most powerful tools for deciphering complex phenomena. When this collective intelligence is artificially constrained by institutional gatekeeping, we all lose the opportunity to benefit from diverse perspectives and approaches. This is particularly true in the case of 3i Atlas, where understanding the object's true nature may require expertise from multiple disciplines: astronomy, physics, engineering, materials, science, and even fields like sociology and philosophy if the object turns out to have artificial characteristics. By restricting access to data, institutions limit the cross-pollination of ideas that often leads to breakthrough insights. The public's right to know isn't just about abstract principles of transparency, it's about practical consequences as well. Discoveries about interstellar objects could have implications for planetary defense, resource utilization, and even long-term survival strategies for humanity. If 3i Atlas or similar objects represent technologies or physics we don't understand, then public awareness and engagement become essential for developing appropriate responses and policies. Without transparency, we risk creating a situation where a small group of insiders makes decisions that affect everyone's future without public input or accountability. The digital age has transformed the landscape of scientific communication in ways that both challenge and enable transparency. On one hand, the internet and social media have created channels for information to spread rapidly, bypassing traditional institutional gatekeepers. This makes it harder for agencies to control narratives and maintain secrecy. On the other hand, the same channels can be used to spread misinformation and create confusion around legitimate scientific findings. In this context, institutional silence becomes particularly problematic when official channels are quiet, unofficial. Sources fill the vacuum with speculation, conspiracy theories, and misinformation. The best way to combat this isn't to restrict information further, but to increase transparency, providing accurate, timely information that can ground public discussion in reality rather than speculation. The case of 3i Atlas suggests we need new frameworks for scientific transparency in an age when discoveries may have profound societal implications. These frameworks should include default transparency protocols that require automatic release of data within specified timeframes, with exceptions only for clearly defined and limited circumstances. Independent oversight committees with public representation to review decisions to withhold or delay information. Clear criteria for what constitutes information that can be justifiably restricted. With regular review of these criteria, mechanisms for gradual declassification of sensitive information, similar to those used for national security, documents, public engagement processes that allow society to participate in discussions about the implications of major discoveries, international agreements on transparency standards for space science, particularly in cases involving potential discoveries of extraterrestrial technology or intelligence. Implementing such frameworks would require a cultural shift within scientific institutions, from viewing the public as passive recipients of knowledge to seeing them as partners in the discovery process. It would require balancing legitimate concerns about accuracy and stability with the ethical imperative of transparency. Most importantly, it would require recognizing that in an age when scientific discoveries may reshape humanity's future, the public's right to know isn't just a nice principle, it's essential for democratic governance and responsible progress. The story of 3I Atlas may ultimately be remembered not for what the object was, but for how we responded to the questions it raised. Did we retreat into institutional silence, or did we embrace transparency? Did we allow a small group of insiders to control knowledge that affects everyone, or did we create systems for open inquiry and public engagement? The answers to these questions will say as much about us as a civilization as any discovery about objects traveling through our solar system. Part 18. The Psychological Dimensions of Cosmic Revelation. The institutional silence surrounding 3I Atlas isn't merely a matter of bureaucratic procedure or scientific protocol. It reflects deep psychological factors that influence how we collectively respond to discoveries that challenge our fundamental understanding of reality. These psychological dimensions help explain why even well-intentioned institutions might default to caution and concealment when confronted with anomalies that could reshape our cosmic perspective. At the individual level, scientists and institutional leaders are human beings subject to the same cognitive biases and emotional responses as anyone else. When confronted with data suggesting something as extraordinary as an artificial interstellar object, even the most rational minds experience cognitive dissonance, psychological discomfort that arises when new information conflicts with deeply held beliefs. This discomfort creates a powerful motivation to find conventional explanations, to question the data, or to delay acceptance until the anomaly can be reconciled with existing frameworks. The professional culture of science amplifies this tendency. Scientific careers are built on careful, incremental advances with an established paradigm. Researchers who challenge fundamental assumptions often face skepticism, reduced funding opportunities, and professional marginalization. This creates a systemic incentive to interpret anomalous data conservatively, to propose natural explanations, even when they require convoluted reasoning, and to avoid making extraordinary claims without overwhelming evidence. While this conservatism serves as a valuable check against premature conclusions, it can also become a barrier to recognizing genuine paradigm shifts. At the institutional level, organizations like NASA and ESA face additional psychological pressures. These agencies have spent decades building public trust through carefully managed communications that emphasize reliability, predictability, and scientific rigor. Discoveries that suggest the presence of extraterrestrial technology or unknown physics threaten to undermine this carefully constructed image of control and competence. The psychological need to maintain institutional credibility can create a powerful incentive to frame anomalous findings in the least disruptive terms possible. The public's psychological response to potential cosmic revelations adds another layer of complexity. History shows that humanity has a complicated relationship with the idea of extraterrestrial intelligence. While many people express curiosity and even enthusiasm about the possibility, others experience deep anxiety, existential dread, or religious conflict. The prospect that we might not be alone in the universe, or that we might be technologically primitive compared to other civilizations, shares fundamental questions about human significance, purpose, and security. Institutional leaders are acutely aware of these potential public reactions. The psychological burden of potentially triggering widespread anxiety, social disruption, or loss of faith in established institutions creates a powerful motivation for caution. This isn't necessarily paternalistic condescension, but a genuine concern for social stability that shapes decision-making processes around potentially paradigm-shifting discoveries. The media environment adds further psychological complexity. In an era of instant communication and 24-hour news cycles, scientific institutions face the challenge of communicating nuanced findings to a public accustomed to simple narratives and dramatic headlines. The psychological fear of being misunderstood, sensationalized, or misrepresented can lead to overcorrection in the opposite direct and excessive caution, minimal communication, and avoidance of potentially controversial topics. These psychological factors combine to create what might be called a collective inhibition around certain types of discoveries. Even without explicit coordination or conspiracy, individuals and institutions can arrive at similar patterns of behavior based on shared psychological responses to anomalous data. This helps explain why we might see consistent patterns of silence, delay, and minimization across multiple agencies and countries when confronted with phenomena like Three-Eye Atlas. Understanding these psychological dimensions doesn't excuse the lack of transparency, but it does suggest that addressing the problem requires more than just policy changes. We need to develop cultural and psychological frameworks that can help both scientists and the public process potentially reality-shifting discoveries in constructive ways. For the scientific community, this might include training in cognitive BIAS awareness and techniques for overcoming psychological resistance to anomalous data, professional recognition and reward structures that value careful investigation of anomalies rather than only incremental advances within established paradigms. Support systems for researchers who pursue unconventional interpretations of data, protecting them from professional marginalization. Interdisciplinary collaboration that brings diverse perspectives to bear on anomalous findings, reducing the risk of groupthink within specialized fields for institutions. This might involve communication strategies that acknowledge uncertainty while still sharing information transparently, public education initiatives that help society develop psychological resilience to potentially disruptive discoveries, collaboration with experts in psychology, sociology, and communication to develop more effective approaches to sharing paradigm-challenging information. Internal cultures that normalize discussion of extraordinary possibilities, reducing the psychological discomfort associated with such topics for the public. This could include educational resources that help people understand the scientific process and the provisional nature of knowledge, opportunities for public engagement with scientific questions, creating a sense of participation rather than passive reception of information, support for critical thinking skills that can help evaluate extraordinary claims without immediate acceptance or rejection. Forums for discussing the philosophical and societal implications of potential discoveries, helping to process the psychological impact collectively rather than individually. The case of 3i Atlas suggests that we're at a critical juncture in humanity's relationship with the cosmos. As our observational capabilities continue to advance, we're increasingly likely to encounter phenomena that challenge our fundamental assumptions. Our ability to respond productively to these encounters depends not just on our technological sophistication, but on our psychological readiness as individuals, institutions, and societies. The psychological dimensions of cosmic revelation remind us that scientific progress isn't just about gathering data and developing theories. It's about the human capacity to expand our understanding of reality, even when that expansion challenges our most fundamental beliefs. By recognizing and addressing the psychological barriers to transparency, we can create a more resilient scientific culture that remains open to extraordinary possibilities without sacrificing rigor or credibility. In the end, how we psychologically prepare for and respond to potential cosmic revelations may say as much about our maturity as a civilization as the discoveries themselves. The silence surrounding 3i Atlas isn't just a matter of missing data, it's a reflection of our collective psychological relationship with the unknown and our readiness to embrace a potentially much larger and more complex universe than we've imagined. Part 19. The technological imperative preparing for future encounters. The saga of 3i Atlas and the institutional response to its anomalies highlights a critical gap in our preparedness for future encounters with potentially extraordinary cosmic phenomena. As our observational capabilities continue to advance exponentially, we're entering an era where the discovery of objects or phenomena that challenge our understanding of the universe becomes increasingly likely. The question is whether our technological, institutional, and social frameworks are ready to handle such discoveries in a way that maximizes scientific understanding while minimizing disruption and maintaining public trust. The technological dimension of this preparedness challenge is perhaps the most straightforward to address. We need observation systems specifically designed to capture detailed data about anomalous objects without the technical limitations and institutional constraints that have hampered our investigation of 3i Atlas. This includes dedicated, repeat response observation platforms that can be quickly retasked to study newly discovered interstellar objects or unusual phenomena. Unlike current spacecraft that have limited maneuverability and fixed observation schedules, these platforms would be designed specifically for flexibility and rapid response. Advanced imaging systems, capable of capturing high-resolution data across multiple spectra simultaneously. The limitations of single-purpose instruments have become apparent in the 3i Atlas case, where different spacecraft captured different pieces of the puzzle. But no single platform had the comprehensive capability needed to understand the object fully. Automated data processing systems with transparent algorithms that can identify anomalies without hiding them from human research. The current AI filtering systems may inadvertently suppress the very discoveries we're most eager to find. We need systems that flag anomalies for immediate human review rather than routing them into indefinite quarantine. Redundant data collection and storage systems that prevent the kind of mysterious data gaps we've seen with the Psyche mission. Multiple, independent pathways for data transmission and storage would make it much harder for technical issues or institutional decisions to result in complete information blackouts. International observation networks that can coordinate observations across multiple agencies and countries. The 3R Atlas case has shown how different agencies can arrive at similar patterns of data restriction independently. A coordinated international approach with shared protocols for transparency could help counteract this tendency. Beyond the technological requirements, we need institutional frameworks that can handle potentially paradigm-shifting discoveries more effectively than our current systems. These frameworks should include pre-established protocols for data classification and release that balance legitimate security concerns with the imperative for scientific transparency. These protocols should be developed in advance with public input rather than improvised in response to specific discoveries. International agreements on information sharing for potentially sensitive astronomical discoveries. Just as we have protocols for sharing data about potentially hazardous asteroids, we need similar agreements for objects or phenomena that might have technological or intelligence implications. Independent review boards with diverse expertise, scientists, ethicists, communication specialists, and public representatives to evaluate decisions about restricting or delaying information release. These boards would provide external oversight and accountability for institutional decisions. Communication strategies specifically designed for sharing extraordinary discoveries with the public, rather than defaulting to silence or minimal disclosure. Institutions should have plans for gradually introducing potentially disruptive information in ways that maximize understanding while minimizing panic. Mechanisms for rapid peer review and validation of extraordinary findings. One of the justifications for delaying release of anomalous data is the need for thorough verification. We need systems that can accelerate this process without sacrificing rigor when the potential significance of findings warrants it. The social dimension of preparedness is perhaps the most challenging but also the most important. Society's ability to process and integrate potentially reality-shifting discoveries depends on developing greater scientific literacy, critical thinking skills, and psychological resilience. This includes educational initiatives that help people understand the nature of scientific inquiry, including its provisional nature and its capacity to revise understanding based on new evidence. Public forums for discussing the philosophical and societal implications of potential discoveries before they occur. By engaging with these questions in advance, we can reduce the shock and disorientation that might accompany actual paradigm-shifting discoveries. Media literacy programs that help people evaluate extraordinary claims and distinguish between credible sources and misinformation. This is particularly important in an era when sensationalism can spread rapidly through digital channels. Support systems for helping individuals and communities process the psychological impact of potentially disruptive discoveries. Just as we have mental health resources for dealing with personal trauma, we may need similar resources for dealing with collective existential challenges, democratic processes for making decisions about how to respond to discoveries that might affect humanity's future, questions about whether to attempt communication with potential extraterrestrial intelligence, how to allocate resources for further investigation, and what precautions to take should be made through inclusive deliberation rather than by small groups of insiders, the technological imperative for future preparedness extends beyond just observation systems to include the development of theoretical frameworks that can accommodate phenomena that might not fit our current understanding of physics. If 3i Atlas or similar objects represent technologies or physical principles beyond our current knowledge, we need theoretical approaches that can recognize and investigate such possibilities without automatically dismissing them as impossible. This might involve greater interdisciplinary collaboration between physicists, engineers, materials scientists, and other specialists who might recognize patterns that specialists in a single field might miss. Theoretical work that explores the boundaries of known physics and considers how technologies might operate within or slightly beyond those boundaries. Computational modeling that can simulate a wider range of potential behaviors and characteristics for anomalous objects, helping us recognize patterns we might not otherwise anticipate. Historical research into previous scientific paradigm shifts to understand how similar transitions have occurred in the past and what we might learn from them. The 3i Atlas case has shown us that we're not adequately prepared for the discovery of objects or phenomena that might fundamentally reshape our understanding of the universe. The technological, institutional, and psychological gaps this case reveals represent not just challenges, but opportunities to develop more robust observation systems, more transparent institutional practices, and more resilient social frameworks for processing extraordinary discoveries as we continue to advance technologically and expand our observational capabilities. The likelihood of encountering phenomena that challenge our current understanding increases. Whether these phenomena turn out to be unusual natural objects, artifacts of extraterrestrial technology, or manifestations of physics we don't yet comprehend, our ability to respond productively depends on the preparations we make today. The technological imperative isn't just about building better telescopes or spacecraft, it's about creating comprehensive systems of observation, analysis, communication, and decision-making that can handle the full range of possibilities we might encounter as we continue to explore the cosmos. By learning from the silences and delays surrounding 3i Atlas, we can develop more effective approaches to future encounters that balance caution with curiosity, skepticism with openness, and institutional stability with the imperative for discovery. Part 20. The philosophical implications, imagining our cosmic context. The mysteries surrounding 3i Atlas and the institutional response to its anomalies ultimately forces us to confront deeper philosophical questions about humanity's place in the cosmos and how we construct knowledge about reality. These questions extend beyond the specific characteristics of one interstellar object to touch on fundamental aspects of epistemology, ontology, and the sociology of knowledge in an age of potentially paradigm-shifting scientific discoveries. the most basic level, the 3i Atlas case challenges our assumptions about the relationship between observation and understanding. In traditional scientific practice, we operate on the principle that careful observation leads to accurate understanding, and that sharing data openly accelerates the collective process of knowledge building. The pattern of silence, delay, and selective disclosure surrounding 3i Atlas suggests a breakdown in this relationship, where observation occurs but understanding is constrained by institutional filters rather than the inherent limitations of the data itself. This situation raises fundamental epistemological questions. What constitutes valid knowledge when potentially paradigm-shifting observations are subject to institutional gatekeeping? How do we distinguish between legitimate scientific caution and problematic knowledge suppression? Who gets to decide which observations become part of our collective understanding of reality, and by what authority? The ontological implications are equally profound. If 3i Atlas represents something beyond our current categories of natural objects, perhaps technology of non-human origin, or physics we don't yet comprehend, then our entire framework for categorizing and understanding reality may need revision. The difficulty institutions have shown in processing and sharing information about the object suggests we may be operating with conceptual categories too rigid to accommodate the full complexity of cosmic reality. This rigidity reflects what philosophers might call a category error applying frameworks developed for understanding terrestrial and familiar phenomena to phenomena that may operate according to entirely different principles. Just as pre-Copernican astronomy struggled to accommodate observations that didn't fit within an Earth-centered model, our current scientific institutions may be struggling to process observations that don't fit within a paradigm that assumes natural, non-intelligent explanations for cosmic phenomena. The sociology of scientific knowledge offers additional insights into the 3i Atlas situation. Scientific knowledge doesn't advance solely through the accumulation of data. It progresses through social processes involving negotiation, consensus building, and the resolution of conflicts between competing interpretations. The institutional silence surrounding 3i Atlas represents a disruption of this social process, preventing the normal negotiation of meaning that occurs when the scientific community collectively works to understand anomalous findings. This disruption has consequences beyond the specific case of one interstellar object. It potentially establishes precedents for how institutions respond to future anomalies, creating patterns of behavior that may become normalized over time. If institutional silence becomes an accepted response to potentially paradigm-challenging discoveries, we risk creating a scientific culture that prioritizes stability over discovery, conformity over creativity, and institutional preservation over the advancement of knowledge. The ethical dimensions of this situation are equally significant. If institutions funded by the public are making decisions about withholding information that could reshape humanity's understanding of its place in the cosmos, what ethical framework justifies such decisions? The traditional principles of research ethics emphasize transparency, informed consent, and the responsible communication of findings. The pattern of behavior surrounding 3i Atlas appears to violate these principles, suggesting a need to reconsider how we apply ethical frameworks to potentially paradigm-shifting scientific discoveries. The political implications cannot be ignored either. In democratic societies, scientific institutions operate with public funding and public trust. When these institutions make decisions to restrict or delay information without public input or accountability, they undermine the democratic contract that underpins their existence. This creates a dangerous precedent where unelected officials make decisions about what the public is allowed to know, potentially without legitimate justification. The cultural dimensions of how we process potentially reality-shifting discoveries are equally important. Different cultures may respond very differently to the possibility of extraterrestrial technology or intelligence. Some might embrace it as evidence of cosmic abundance and opportunity. Others might perceive it as threatening to fundamental beliefs about human uniqueness or specialness. The institutional tendency toward caution and concealment may reflect an unconscious bias toward preserving existing cultural frameworks rather than allowing them to evolve in response to new information. The religious implications of potentially paradigm-shifting discoveries are equally profound. Many religious traditions have developed cosmologies that place humanity in a special relationship with the divine. Discoveries that suggest we might not be alone in the universe, or that we might be technologically primitive compared to other civilizations, could challenge these cosmologies in fundamental ways. The institutional silence surrounding 3i Atlas may partly reflect an unconscious desire to avoid triggering religious conflicts or existential crises. The psychological dimensions of how we collectively process potentially reality-shifting information connect to these philosophical questions. The human mind has evolved to understand reality at scales and in contexts that were relevant to our survival as a species. Encountering phenomena that operate across cosmic timescales, distances, and potentially with technologies beyond our comprehension may stretch our cognitive capacities to their limits. The institutional tendency toward caution and concealment may partly reflect an intuitive recognition that humanity as a whole may need time to psychologically prepare for and integrate potentially reality-shifting discoveries. The educational implications are equally significant. Our current educational systems generally present scientific knowledge as relatively settled and complete, with occasional adjustments at the margins. The possibility that we might encounter phenomena that fundamentally challenge our understanding of reality suggests we need educational approaches that emphasize the provisional nature of knowledge, the importance of intellectual humility, and the capacity to revise our understanding in response to new evidence. The artistic and creative dimensions of how we process potentially reality-shifting discoveries shouldn't be underestimated either. Throughout history, artists have often been ahead of scientists in imagining possibilities that later became reality. The institutional silence surrounding 3i Atlas may be depriving the creative community of the raw material needed to help society process and integrate potentially paradigm-shifting discoveries through artistic expression. Ultimately, the philosophical implications of the 3i Atlas case call us to reconsider how we construct knowledge about reality in an age when our observational capabilities are increasingly likely to encounter phenomena that challenge our fundamental assumptions. This requires developing more flexible conceptual frameworks, more transparent institutional practices, and more resilient social and psychological approaches to processing potentially reality-shifting discoveries. The cosmos has always operated according to principles that transcend human understanding and institutional convenience. As we continue to develop the technological capacity to observe more of the universe in greater detail, we inevitably increase the likelihood of encountering phenomena that don't fit our existing categories and explanations. How we respond to these encounters, whether with intellectual courage and transparency or with fear and concealment, will say as much about our maturity as a civilization as the discoveries themselves. The philosophical challenge posed by 3i Atlas isn't just about understanding what this particular object might be. It's about developing the wisdom, humility, and flexibility needed to expand our understanding of reality, while maintaining the social and psychological cohesion necessary for humanity to thrive in a universe that may be far stranger and more complex than we've imagined. Part 21. The Road Ahead, Charting a Course for Cosmic Transparency. As we reflect on the mystery surrounding 3i Atlas and the institutional patterns of silence, delay, and selective disclosure that have characterized our response to this anomalous visitor, we must look forward to how we might handle future encounters differently. The road ahead requires not just technological improvements, but fundamental shifts in our approach to transparency, public engagement, and the very philosophy of scientific discovery in an age of potentially paradigm-shifting revelations. The first step on this road is acknowledging the limitations of our current approach. The case of 3i Atlas has revealed systemic vulnerabilities in how we collect, process, and share information about anomalous cosmic phenomena. These vulnerabilities include technical gaps in our observation capabilities, institutional tendencies toward caution and concealment, psychological barriers to accepting paradigm-challenging discoveries, and a lack of established protocols for transparent communication of potentially disruptive findings. Addressing these vulnerabilities requires a multifaceted approach that begins with technological innovation but extends to institutional reform, public education, and international cooperation. Each of these dimensions presents its own challenges and opportunities, but together they form a comprehensive framework for cosmic transparency that can better serve both scientific progress and democratic values. On the technological front, we need to develop observation systems specifically designed to study anomalous objects without the limitations that have hampered our investigation of 3i Atlas. This includes spacecraft with greater maneuverability and flexibility, instruments capable of capturing comprehensive data across multiple spectra, redundant data collection and transmission systems, and automated processing that flags anomalies for immediate human review rather than routing them into indefinite quarantine. Beyond hardware, we need software and analytical tools that can help us recognize patterns that might not fit our existing models. Machine learning systems trained on a broader range of possibilities, including artificial or technological phenomena, help us overcome the cognitive biases that might cause human researchers to dismiss or minimize anomalous data. These systems should be designed with transparency in mind, making their decision-making processes visible and auditable, rather than operating as black boxes that might inadvertently suppress the very discoveries we're seeking. Institutional reform is equally crucial. We need to establish clear protocols for data classification and release that. Balance legitimate security concerns with the imperative for scientific transparency. These protocols should be developed in advance through inclusive processes that involve not just scientists and administrators, but ethicists, communication specialists, public representatives, and legal experts. The principle of default transparency should guide these protocols. Data should be released automatically unless specific, narrowly defined criteria for restriction are met. And even then, restrictions should be time-limited and subject to independent review. The burden of proof should be on those who advocate for secrecy, not on those who demand openness. International cooperation is essential for effective cosmic transparency. The 3 Atlas case has shown how different agencies and countries can arrive at similar patterns of restriction independently, creating a collective suppression of information without explicit coordination. By developing international agreements on information sharing for potentially significant astronomical discoveries, we can create a framework that counteracts the tendency toward institutional caution, while respecting legitimate national security. Concerns. Public engagement and education represent another critical dimension of the road ahead. We need to develop greater scientific literacy and critical thinking skills that can help society process potentially disruptive discoveries without panic or denial. This includes educational initiatives that help people understand the nature of scientific inquiry, its provisional character, and its capacity to revise understanding based on new evidence. Media literacy is equally important in an era when misinformation spreads rapidly through digital channels. We need to help people evaluate extraordinary claims and distinguish between credible sources and sensationalism. This isn't about controlling the narrative, but empowering people to engage with complex information thoughtfully and critically. Public forums for discussing the philosophical and societal implications of potential discoveries can help prepare society for paradigm shifts. By engaging with questions about humanity's place in the cosmos before definitive discoveries occur, we can reduce the shock and disorientation that might accompany actual revelations. The psychological dimension of preparing for future encounters requires attention as well. We need support systems for helping individuals and communities process the existential impact of potentially reality-shifting discoveries. This might involve mental health resources, community discussion groups, and other mechanisms for collective processing of extraordinary information. The ethical framework guiding our approach to future encounters must prioritize transparency, accountability, and the public's right to know. Decisions about restricting or delaying information should be subject to ethical review that considers not just institutional interests, but broader societal values. The default position should be openness, with restrictions applied only when absolutely necessary and for limited periods. The political dimension of cosmic transparency requires democratic oversight of institutions that make decisions about information release. We need mechanisms for public accountability that ensure agencies funded by taxpayers are responsive to public values and priorities. This might involve congressional or parliamentary oversight committees with appropriate expertise, public reporting requirements, and processes for public input into policy decisions. The cultural dimension of preparing for future encounters shouldn't be underestimated either. Different cultures may respond very differently to potentially paradigm-shifting discoveries. We need approaches that respect cultural diversity while finding common ground for international cooperation. This might involve cross-cultural dialogue, educational exchanges, and collaborative projects that build trust and understanding across national and cultural boundaries. The artistic and creative dimensions of processing. Potentially reality-shifting discoveries offer valuable opportunities. As well, artists can help society visualize and emotionally integrate possibilities that might initially seem threatening or incomprehensible. Supporting artistic engagement with cosmic questions can enrich our collective imagination and emotional resilience. The religious dimension of preparing for potential discoveries requires thoughtful engagement as well. Rather than seeing scientific discoveries as threats to religious belief, we can foster dialogue between scientific and religious communities that explores how new knowledge might be integrated into existing worldviews or inspire new ones. This dialogue can help reduce potential conflicts and promote a more nuanced understanding of the relationship between scientific and spiritual ways of knowing. The educational dimension of preparing for future encounters extends beyond formal education to include informal learning opportunities for people of all ages. Museums, science centers, planetariums, and other institutions can play important roles in helping the public engage with cosmic questions and develop the knowledge and skills needed to process potentially paradigm-shifting discoveries. The road ahead for cosmic transparency won't be easy. It requires overcoming institutional inertia, challenging established power structures, and confronting uncomfortable possibilities. But the alternative, a future where potentially reality-shifting discoveries are hidden from public view, where a small group of insiders decides what humanity is allowed to know about its place in the cosmos, is far more dangerous in the long run. By learning from the silences and delays surrounding 3i Atlas, we can develop more effective approaches to future encounters that balance legitimate concerns with the fundamental values of transparency, accountability, and democratic participation. The cosmos doesn't operate according to human institutional preferences or psychological comfort zones. As we continue to develop the capacity to observe more of the universe in greater detail, we inevitably increase the likelihood of encountering phenomena that challenge our understanding of reality. How we respond to these encounters will say as much about our maturity as a civilization as the discoveries themselves. Will we retreat into institutional silence when confronted with the extraordinary, or will we embrace transparency with courage and humility? Will we allow a small group of insiders to control knowledge that affects everyone's future, or will we create systems for open inquiry and democratic deliberation? The road ahead offers us an opportunity to demonstrate that humanity can handle the truth about our cosmic context, whatever that truth might be, by developing the technological, institutional, psychological, and ethical frameworks for cosmic transparency. We prepare ourselves not just for future discoveries, but for the continued evolution of our understanding of reality and our place within it. Part 22. The personal dimension: how cosmic discoveries transform individual lives. While we've examined the institutional, technological, and societal dimensions of the 3i Atlas mystery, we must also consider how potentially paradigm-shifting discoveries affect individuals on a personal level. The story of this anomalous interstellar visitor isn't just about missing data points or institutional silences, about how each of us might be called to reconsider our place in a cosmos that may be far stranger and more populated than we've imagined. The personal impact of cosmic revelations begins with a fundamental human need to make sense of our existence. Throughout history, we've constructed narratives that help us understand who we are, why we're here, and what our purpose might be. These narratives, whether religious, philosophical, or scientific, provide frameworks for meaning that help us navigate the challenges of life, discoveries that suggest we might not be alone in the universe, or that we might be technologically primitive compared to other civilizations, can shake these frameworks to their core. For some, this shaking might be experienced as liberation and an exciting expansion of possibilities that opens new horizons for imagination and exploration. For others, it might feel like a profound loss of specialness, of purpose, of the comforting belief that humanity occupies a privileged position in the cosmic scheme. The psychological journey of integrating potentially reality-shifting discoveries is deeply personal and varies widely based on individual temperament, background, and existing belief systems. The emotional dimension of this journey deserves careful attention. Feelings of awe, wonder, excitement, and curiosity often accompany the consideration of extraordinary cosmic possibilities. These emotions can be exhilarating and motivating, inspiring us to learn more and engage more deeply with questions about the universe. But they may be accompanied by feelings of anxiety, fear, confusion, or even grief as familiar worldviews give way to new and uncertain understandings. The cognitive dimension of processing potentially paradigm-shifting discoveries involves intellectual challenges as well. Our minds have evolved to understand reality at scales and in contexts that were relevant to our survival as a species. Encountering phenomena that operate across cosmic timescales, distances, and potentially with technologies beyond our comprehension, can stretch our cognitive capacities to their limits. The mental effort required to expand our understanding of reality can be both exhilarating and exhausting. The social dimension of how individuals process cosmic discoveries shouldn't be underestimated either. Our beliefs about the cosmos don't exist in isolation. They're embedded in relationships with family, friends, communities, and cultural groups. When our understanding of reality shifts, it can create tensions with those who don't share our new perspective. These social dynamics can add layers of complexity to the personal journey of integrating potentially paradigm-shifting discoveries. The spiritual dimension of this journey is equally significant for many people. Questions about humanity's place in the cosmos have always been intertwined with spiritual and religious traditions. Discoveries that might suggest the existence of extraterrestrial intelligence or technologies beyond our current understanding can challenge these traditions in profound ways. Some individuals might find ways to integrate new cosmic knowledge into existing spiritual frameworks, while others might feel called to develop entirely new approaches to spiritual meaning. The creative dimension of responding to potentially reality-shifting discoveries offers both challenges and opportunities. Artists, writers, musicians, and other creative individuals often play crucial roles in helping society process and integrate new understandings of reality. On a personal level, engaging creatively with cosmic questions can provide meaningful ways to explore and express the emotional and intellectual dimensions of paradigm shifts. The practical dimension of how cosmic discoveries might affect individual lives is worth considering as well. While questions about interstellar objects or extraterrestrial technology might seem abstract and distant, they could eventually have practical implications for how we live our lives. Discoveries about new physics or technologies might inspire new career paths, educational choices, or investment decisions. Even the psychological impact of knowing we might not be alone in the universe could influence how we approach relationships, community building, and long-term planning. The ethical dimension of personal responses to potentially paradigm-shifting discoveries deserves attention too. As individuals grapple with new information about the cosmos, they face questions about how to act on this knowledge. Should they share it with others? How should they balance skepticism and openness? What responsibilities come with potentially extraordinary knowledge? These ethical considerations add another layer of complexity to the personal journey of cosmic discovery. The generational dimension of how individuals process cosmic revelations is particularly interesting. Younger people who have grown up with science fiction portrayals of cosmic possibilities might integrate certain types of discoveries more easily than older generations whose foundational understanding of the cosmos was formed in a different context. Conversely, younger people might feel more existentially threatened by certain discoveries that challenge their sense of future possibilities. Understanding these generational differences can help us develop more nuanced approaches to public engagement and education. The cultural dimension of personal responses to cosmic discoveries reminds us that not everyone experiences potentially reality-shifting information in the same way. Different cultural backgrounds provide different frameworks for understanding humanity's place in the cosmos. What feels like an exciting possibility to someone from one cultural context might feel like a profound threat to someone from another. Recognizing and respecting these differences is essential for developing inclusive approaches to cosmic transparency. The psychological resilience dimension of preparing for potentially paradigm-shifting discoveries is crucial as well. Some individuals naturally possess greater psychological flexibility and are better able to tolerate uncertainty and ambiguity. Others may struggle more with questions that don't have clear answers or that challenge fundamental assumptions. Developing psychological resilience through practices like mindfulness, community support, and cognitive flexibility can help individuals navigate the personal journey of cosmic discovery. The educational dimension of personal preparation for potentially reality-shifting discoveries is equally important. Individuals with stronger foundations in critical thinking, scientific literacy, and philosophical reasoning may be better equipped to evaluate extraordinary claims and integrate new information without either uncritical acceptance or rigid rejection. Lifelong learning habits can help people stay open to new possibilities while maintaining appropriate skepticism. The community dimension of how individuals process cosmic discoveries shouldn't be underestimated either. While the journey of integrating Potentially reality-shifting information can feel deeply personal. It often happens most effectively in community with others who are asking similar questions. Support groups, discussion circles, online forums, and other community structures can provide valuable spaces for shared exploration of cosmic questions. The hope dimension of personal responses to cosmic discoveries is perhaps the most important of all. Despite the challenges and potential difficulties of integrating potentially paradigm-shifting information, many people find that expanding their understanding of the cosmos ultimately leads to a greater sense of hope, possibility, and meaning. The recognition that we might be part of a much larger cosmic community, or that the universe might be far more interesting and complex than we've imagined, can inspire renewed commitment to exploration, discovery, and the ongoing project of understanding reality. As we reflect on the personal dimensions of how cosmic discoveries might transform individual lives, we're reminded that the story of 3i Atlas isn't just about institutional silence or missing data. It's about how each of us might be called to expand our understanding of reality and our place within it. This personal journey of cosmic discovery, with all its challenges and opportunities, represents perhaps the most profound dimension of what it means to be human in a universe that continues to surprise and inspire us. Part 23. The call to action, what we can do now. As we've explored the many dimensions of the 3i Atlas mystery, from the technical details of missing data to the philosophical implications of potentially paradigm-shifting discoveries, we arrive at a crucial question. What can we do now? How can each of us, in our own capacities and contexts, contribute to a future where cosmic transparency prevails over institutional silence, where curiosity triumphs over fear, and where humanity collectively embraces the truth about our place in the cosmos? The first step in this call to action is education, both our own and that of others. The complexity of the 3i Atlas case reminds us that understanding cosmic phenomena requires more than superficial knowledge. We each have a responsibility to deepen our understanding of astronomy, physics, and the scientific process. This doesn't mean we all need to become experts, but we should strive to develop sufficient scientific literacy to evaluate extraordinary claims critically and to recognize when institutional explanations don't quite add up. Educational resources abound for those willing to seek them out. Online courses, documentaries, books, podcasts, and museum exhibits can all help build foundational knowledge. More importantly, we can support science education in our communities, advocating for strong science programs in schools, participating in public science events, and encouraging young people's interest in cosmic questions. By elevating scientific literacy across society, we create a foundation that can support more nuanced public engagement with potentially paradigm-shifting discoveries. The second step is supporting independent research and citizen science initiatives. While institutional agencies play crucial roles in space exploration, they're not the only sources of knowledge about the cosmos. Independent researchers, amateur astronomers, and citizen scientists contribute valuable observations and analyses that sometimes challenge institutional narratives. We can support these efforts through funding, participation, or simply by paying attention to their findings and giving them serious consideration. Crowdfunding platforms have emerged as powerful tools for supporting independent research projects that might not receive institutional funding. By contributing to such projects, we help diversify the sources of knowledge about the cosmos and reduce dependence on institutions that might be subject to political or other pressures. Similarly, citizen science projects that invite public participation in data analysis or observation can help democratize the process of cosmic discovery. The third step is advocating for transparency and accountability from scientific institutions. As taxpayers and members of democratic societies, we have a right to expect that institutions funded with public money will operate transparently and be accountable to the public they serve. This means supporting policies and practices that promote open data, clear communication about limitations and uncertainties, and independent oversight of decisions to restrict or delay information release. We can advocate for these principles through various channels, contacting our elected representatives about science policy, participating in public comment periods for agency decisions, supporting organizations that work for government transparency, and using our voices in public forums to emphasize the importance of open science. When enough people demand transparency, institutions become more responsive to these demands. The fourth step is developing our critical thinking skills and media literacy. In an era of information overload and rapid digital communication, the ability to evaluate sources, recognize bias, and distinguish between credible claims and misinformation has never been more important. We can cultivate these skills through practice, education, and conscious consumption of information. This includes seeking out diverse perspectives on cosmic questions, being willing to change our minds when presented with compelling evidence, and maintaining appropriate skepticism toward extraordinary claims, while remaining open to possibilities that might challenge our existing assumptions. By improving our own critical thinking skills and helping others do the same, we contribute to a more robust public discourse about potentially paradigm-shifting discoveries. The fifth step is engaging in respectful dialogue about cosmic questions. The three artless case, like other potentially paradigm-shifting discoveries, can evoke strong emotional responses and deeply held beliefs, creating space for respectful dialogue where people with different perspectives can share their views without fear of ridicule or dismissal, helps prevent the polarization that can hinder collective understanding. We can create these spaces in our families, communities, workplaces, and online networks. By modeling respectful curiosity and intellectual humility, we encourage others to engage in good faith with complex questions. Even when we disagree with others' interpretations of cosmic phenomena, we can acknowledge the legitimacy of their questions and concerns while maintaining our own critical perspective. The sixth step is supporting artistic and creative engagement with cosmic questions. Artists, writers, musicians, and other creative individuals play crucial roles in helping society process and integrate potentially reality-shifting discoveries. By supporting their work through attendance, purchases, advocacy, or simply sharing their creations, we help create cultural resources that can expand our collective imagination and emotional resilience. Creative engagement with cosmic Questions isn't just about entertainment. It's about developing the cultural vocabulary we need to discuss and understand our place in the cosmos. When we support artists who explore these themes, we're investing in society's capacity to process extraordinary discoveries in ways that go beyond purely intellectual analysis. The seventh step is preparing ourselves psychologically for potentially paradigm-shifting discoveries. The personal journey of integrating new cosmic knowledge can be challenging, even when it's ultimately rewarding. We can develop psychological resilience through practices like mindfulness, community building, and intentional reflection on our relationship with the unknown. This preparation might involve exploring our own beliefs about humanity's place in the cosmos, considering how we might respond to different types of discoveries, and developing support networks that can help us process potentially disorienting information. By doing this inner work in advance, we become better able to navigate the personal dimensions of cosmic discovery with grace and wisdom. The eighth step is building bridges between different communities that might have stakes in potentially paradigm-shifting discoveries. Scientists, religious leaders, educators, policymakers, artists, military personnel, and many other groups all have perspectives and concerns related to cosmic questions, creating opportunities for these communities to dialogue and find common ground can help prevent the conflicts and misunderstandings that might otherwise accompany extraordinary discoveries. We can facilitate this bridge building by participating in interdisciplinary events, supporting organizations that bring different communities together, and being willing to step outside our own comfort zones to understand perspectives that might differ from our own. The more we can develop shared frameworks for discussing cosmic questions, the better prepared we'll be to respond collectively to potentially paradigm-shifting discoveries. The ninth step is maintaining a long-term perspective on cosmic discovery. The 3 Atlas case reminds us that understanding anomalous phenomena often takes time, sometimes years or decades. In our fast-paced culture of instant gratification, we can lose sight of the fact that genuine scientific understanding typically unfolds gradually, with many twists and turns along the way. By maintaining a long-term perspective, we avoid the trap of demanding immediate answers to complex questions and instead support the patient, persistent work of investigation that eventually leads to deeper understanding. This perspective also helps us stay engaged with cosmic questions even when they fade from headlines, recognizing that the most important discoveries often happen away from the spotlight. The 10th and final step is cultivating wonder and curiosity as fundamental orientations toward the cosmos. Regardless of what specific discoveries might await us, approaching the universe with a sense of wonder and curiosity enriches our lives and prepares us to receive new knowledge with openness rather than fear. This orientation doesn't mean abandoning critical thinking or accepting extraordinary claims without evidence. It means maintaining a childlike sense of awe at the vastness and complexity of the cosmos, while still applying adult reasoning to evaluate specific claims. Cultivating wonder and curiosity might involve spending time under dark skies, learning about the latest astronomical discoveries, engaging with science fiction that explores cosmic possibilities, or simply allowing ourselves to be moved by the beauty and mystery of the universe. by nurturing this orientation within ourselves and encouraging it in others, we create the emotional and spiritual foundation needed to embrace whatever truths the cosmos might reveal. Part 24. Conclusion: Embracing our cosmic destiny. As we reach the conclusion of our exploration into the mysteries surrounding Three-Eye Atlas and the institutional patterns of silence, delay, and selective disclosure that have characterized our response to this anomalous visitor, we find ourselves at a threshold not just of understanding this particular object, but of humanity's relationship with the cosmos itself. The story of Three-Eye Atlas is more than a scientific puzzle. It's a mirror reflecting our collective readiness to encounter a universe that may be far stranger, more complex, and more populated than we've imagined. The journey we've undertaken through these 24 parts has taken us from the technical details of missing data and anomalous observations to the philosophical implications of potentially paradigm-shifting discoveries. We've examined institutional behaviors, psychological responses, technological limitations, and ethical considerations. We've explored the personal dimensions of how cosmic discoveries might transform individual lives and considered what each of us can do to contribute to a future of greater cosmic transparency. Throughout this exploration, a central theme has emerged: the tension between the human impulse to control and contain knowledge that might disrupt existing frameworks and the equally human impulse to explore, understand, and expand our horizons. This tension plays out not just in institutions like NASA and ESA, but within each of us as we balance the comfort of familiar narratives with the excitement of new possibilities. The Three-Eye Atlas case has shown us what happens when the impulse to control predominance data goes missing, explanations remain vague, and the public is left with more questions than answers. But it has also shown us the power of curiosity and critical thinking. As independent researchers, citizen scientists, and engaged members of the public have pieced together patterns that challenge institutional narratives. As we move forward from this case, we face a choice about which impulse will guide our collective relationship with the cosmos. Will we retreat into institutional silence when confronted with the extraordinary, or will we embrace transparency with courage and humility? Will we allow a small group of insiders to control knowledge that affects everyone's future, or will we create systems for open inquiry and democratic deliberation? The answer to these questions will shape not just how we understand specific cosmic phenomena, but how we evolve as a civilization. The cosmos doesn't operate according to human institutional preferences or psychological comfort zones. As our technological capabilities continue to advance, we inevitably increase the likelihood of encountering phenomena that challenge our fundamental assumptions about reality. How we respond to these encounters will say as much about our maturity as a species as the discoveries themselves. The universe has been operating for 13.8 billion years without regard for human institutional procedures or psychological readiness. It will continue to surprise and challenge us regardless of how prepared we feel. The most profound implication of the Three-Eye Atlas mystery may be that the universe is trying to tell us something, not just about this particular object, but about the nature of cosmic reality itself. Perhaps the message is that we need to develop greater humility in the face of cosmic complexity, Perhaps it's that we need to reform our institutions to be more transparent and responsive. Perhaps it's that we need to prepare ourselves psychologically for discoveries that might reshape our understanding of our place in the cosmos, whatever the specific message might be. The pattern of anomalies and institutional responses surrounding 3I Atlas serves as a wake-up call, a reminder that we may be on the verge of discoveries that could fundamentally transform human civilization. Whether we're ready for such transformations is, in many ways, up to us. The road ahead requires both technological advancement and institutional reform. But it also requires something more, a shift in consciousness. We need to expand our capacity to hold uncertainty, to entertain possibilities that might initially seem impossible, and to integrate new knowledge without losing our sense of meaning and purpose. This shift in consciousness isn't just about accepting new scientific facts. It's about developing a cosmic perspective that recognizes our interconnectedness with the broader universe and our responsibility to act as wise stewards of the knowledge we gain. It's about balancing scientific skepticism with openness to extraordinary possibilities, institutional caution with the imperative for discovery, and individual perspectives with collective understanding. The 3I Atlas mystery invites us to consider that we might be living in a pivotal moment in human history, a time when our observational capabilities have finally caught up with a cosmos that has been waiting patiently for us to develop the tools needed to perceive its true complexity. Whether we're ready for what we might find is an open question, but the universe won't wait for us to feel comfortable before revealing its secrets. As we conclude this exploration, let us carry forward not just the specific details of the 3I Atlas case, but the broader lessons it offers about transparency, curiosity, institutional accountability, and the human capacity to embrace a larger cosmic understanding. Let us remember that the universe doesn't belong to scientists or institutions. It belongs to all of us, and we all have a role to play in the ongoing project of cosmic discovery. The silence surrounding 3I Atlas may eventually be broken, whether through institutional disclosure, independent research, or future observations that make the anomalies impossible to ignore. When that silence breaks, how we respond will set the tone for humanity's relationship with the cosmos for generations to come. Will we meet the universe with fear and control, or with wonder and openness? Will we hide from truths that might challenge our assumptions, or will we embrace them as opportunities for growth and understanding? Will we allow our institutions to determine what we're allowed to know about our cosmic context? Or will we demand transparency and democratic participation? In the process of discovery, these questions aren't just about 3I Atlas or any other specific cosmic phenomena. They're about who we are as a species and what we aspire to become. The universe has been waiting 13.8 billion years for us to develop the capacity to ask these questions. How we answer them will determine whether humanity takes its next step in cosmic evolution or remains constrained by the limitations of our current understanding. The choice, ultimately, is ours. The cosmos will continue to operate according to its own principles, revealing its secrets gradually but inevitably. Whether we're ready to receive those secrets with wisdom, courage, and humility is up to us. In embracing our cosmic destiny with open minds and hearts, we not only advance scientific understanding, but participate in the grand adventure of consciousness, awakening to its true nature and context. The story of Three Eye Atlas is just one chapter in humanity's larger cosmic journey. Many more chapters await, each with the potential to expand our understanding and transform our perspective. By approaching these chapters with transparency, curiosity, and collective wisdom, we ensure that humanity's cosmic story continues to unfold in ways that honor both our scientific capabilities and our deepest aspirations for meaning and connection. As we look to the stars, whether with telescopes, spacecraft, or simply our sense of wonder, let us remember that we're not just observers of the cosmos, but participants in its ongoing unfolding. The universe is speaking to us in countless ways, through countless phenomena. Whether we're listening, with the attention, humility, and courage required to hear what it's saying remains the ultimate question of our time.